Good evening, Joseph. Good evening.
Good evening.
Yeah, how are you?
Good morning there. I'm good.
Yeah.
I'm good. How are you?
Yeah, fine.
Nice meeting you.
Yeah.
Thank you very much for your
Yeah.
invitation.
Thank you. We have to thank you for presenting your work.
Thank you. Thank you all for inviting me, and thanks Dhanashekhar for contacting for this invitation. So I'm really honored to be here today. It seems very exciting talks you have arranged with the various speakers. No, that's exciting.
Thank you. Thank you so much.
Okay. So please let me know when we'll start. So, and kindly let me know how much time, for my talk. You have 40 minutes or 45. Could you please let me know?
So, Dhanashekhar sir, you have
40 minutes.
Okay, 40 minutes. Okay, okay, great. Thank you.
Dhanashekhar sir and Mike.
Yes, ma'am. Yes, ma'am. Unmuted. 40 minutes is enough, sir. Then discussion. Then to...
Okay, okay.
Shall we start?
Yes, yes. I'm ready. Whenever you are ready, please let me know.
Yes.
Okay. Do you see my slide, Dhanashekhar?
Yes, sir. It is visible. Yes.
Okay.
Perfect.
All right.
Good morning to all. I welcome you all for the day 2, session 3 of second virtual international conference on hierarchically structured materials, ICHSM-2022, organized by the Department of Physics, SRM Institute of Science and Technology, Ramapuram, Chennai. Now I request Dr. M. Dhanashekhar, Assistant Professor, Department of Physics, to introduce Dr. Suprem Das, Assistant Professor, Department of Industrial and Manufacturing Systems Engineering, Kansas State University, Manhattan, KS, USA.
Yes.
Dhanashekhar sir.
Yes, ma'am. Thank you, ma'am.
Yes.
Very good morning, everyone. It's my privilege to introduce Professor Suprem Das, Department of Industrial and Manufacturing System Engineering, Kansas State University, USA. Professor Das received his BS and MS degree theoretical in physics from Utkal University in India and a MS degree experimental in physics from University of Puerto Rico, Rio Batras campus. And then he received a PhD degree in physics from Purdue University. He did a short postdoctoral study at Purdue Electrical and Computer Engineering, and then he moved to Mechanical Engineering Department at Iowa State University as a postdoctoral researcher, while he was also affiliated with the Division of Material Science and Engineering at US Department of Energy Laboratories. After a 2.5 years experience there, fall 2019, he joined Kansas State University as a faculty. Currently, he is running his research program at the Carroll I College of Engineering. He has received University President Mentoring Award, Keystone Research Scholarship, and Jeffrey and Joy Lesman, Carol and Mary Ice named professorship. He has also awarded with major research grant from US National Science Foundation, Department of Energy, Department of Defense, and also private companies. At Kansas State University, he also enjoys bringing his research-based learning to classroom teaching by designing new elective course on graphene and carbon nanomaterial as well. Now I request Professor Das to deliver his presentation. Sir?
Okay. Okay. Good morning. Thank you, Dr. Dhanashekhar, for your kind invitation. And thank you, in fact, all of you for your invitation to this exciting conference. Again, many thanks from here from Manhattan. So today I'm going to talk about some of the research that we are doing here in my lab. And when I first heard about this conference from Dhansekar, I was thinking, what could be a good topic for hierarchical structure? And then immediately came to mind that, oh, we should talk about our work on the graphene, hexagonal boron nitride, graphene and hexagonal boron nitride, because that's the ultimate nanoscale hierarchical structure one can imagine, but a single atomic layer, those kind of features. So in fact, I am really glad to see how our research could be explained to a broader audience in this conference or in this our session. So most of our research that I will be talking about today, so that could be found in this reference that we recently published. So if you are more interested, so please have a look at it, and you can send me an email if you want to talk more about this work. The work is about, as I said, hexagonal boron nitride, graphene hexagonal boron nitride. It's called a heterostructure, nanoscale, truly nanoscale heterostructure. But it's not just a material. How we exploit this high purity and high interface quality material to make state-of-the-art devices from, in particular, transistor type of devices, and how we understand the device physics out of it. That's the goal of my talk today. So before I go to our own research data, let me first give a broader view of our research. So primarily my group here at Kansas State University is focusing on this 2D materials, and a big part of that that we are doing here is about graphene and boron nitride, molybdenum disulfide, molybdenum diselenide. These kind of materials, these are electronic materials, but we are primarily interested because, as you know, you can very much control the thickness up to single atomic layer. Right. So let's focus on the graphene, because today's talk is about graphene. So I'd like to talk about carbon nanomaterials. Carbon nanomaterials is not new. It is decades long old. In fact, in 1985, as you can see, let me bring my laser pointer. Let's see, where can I find the laser pointer? Do you see my cursor, Dhansekar?
Yes, Professor.
Okay. So maybe I can use my cursor. So as you can see, in 1985, Fullerene came into the picture, and there was no big news about fullerenes in the early days, primarily because when something new as a material, a lot of physics and chemistry, right? So in 1985, and still fullerene is a very, very active material in technologies like solar cell, like most of the solar cell research that you'll find, they use fullerene as a charge carrier conduction layer. And that's just one example. Then coming to carbon nanotube in 1991, discovered in IBM lab, and also in Rice University, like places like that in Japan. So carbon nanotube, when it comes to the picture, people think that it's a strange material, but upon high resolution transmission electron microscope and with the imaging, truly it was demonstrated that it's a rolled version of so-called graphene. So in principle, experimentally, graphene was realized from that day when carbon nanotube was discovered. It's just because it was in the reverse way. It was a rolled version of carbon nanotube, of graphene, but nobody still knew really how to isolate this one atom layer carbon, which is graphene. So obviously, before 2004, there are a lot of people who are trying to isolate that, but never been succeed to to isolate truly single layer until 2004, when we heard by Andrew Gaim and Novoselov, this one layer of carbon atom, really high purity, because they used a so-called exfoliation technique to take from a high quality graphite and isolated them into this graphene. And since then, like a lot of physics and chemistry, and now really graphene field is so much expanded. You can pretty much think about any type of application from graphene. So there are two types of things going on now. People are largely thinking about what can we do with the graphene, but also fundamental physics will never will disappear, and many people still looking at physics of graphene, of course, with certain focus, but also there are a lot many other graphene related or carbon related nanomaterials that are still coming up, right? But that's about the material science, how new materials come into the picture, but it is tightly connected to the physics. For example, if you look at the fullerene atom or molecule here, it has a band structure, say homo and LUMO type, people talk about that. And you can think of, if you're a solid state physicist, you can think about a band gap, right? But if you have a carbon nanotube, it's a little bit complex because you have so-called chirality. And depending on the chirality, it can be semiconducting or it can be metallic. And of course, if it is semiconducting, you have a band gap. But if it is metallic, as you can see here, your field band is up to the Fermi level or beyond the Fermi level. So it becomes the metallic, either this type or the band overlapping, depending on what type of chirality within this metallic. But basically, the bottom line is that you have enough charge carriers in the conduction band or above the Fermi level, whereas here you have a finite band gap. Now, if you look at a graphene, it's completely different. The band structure is completely different. It's a linear, or you can say conical at Fermi level. It's just very, very linear. And this is the first time that people saw this linear band structure. And that is the beauty, that is the speciality, and that's is the single most reason why graphene is so different from other materials. But having almost 17, 18 years of discovery, it's not just graphene. The discovery of a graphene gave rise to a series of materials, diverse materials. They are classified as 2D materials, but within 2D, you can find semi-metal, you can find insulator, you can find metallic, you can find superconducting, you can find different types of topology, topological insulators, wildly fermions. There are so many physics, just graphene brought into the picture. So in terms of the application, it takes, of course, as we know all, it takes years to bring into the real application. For example, carbon nanotube was discovered in 1991, but still it has to come to mainstream electronic industry. But people have demonstrated recently that you can make carbon nanotube chip with no silicon, all the functional devices or transistors, they're made of carbon nanotubes. So it takes decades. So I'm very hopeful that graphene will take much less time to come to the market, probably not to the computer, the chip for CMOS applications, but many other applications. And some of them, I am going to talk about that today in my talk. And if you're interested to look at this, you can see these two papers. Now, a little bit about the physics, why graphene is so unique. As I said, the band structure at the Dirac point is called Fermi level. It's called Dirac point because the charge carriers can be very fast. in terms of their mobility at this point, because look at the band structure, it's very conical. So if you calculate the group velocity at this point, it becomes extremely high compared to the normal materials, other materials. So that's why this is so-called Dirac material. But this is a STM image, and this is the real space image, and from solid state physics, from our classroom knowledge. If you look at the Brillouin zone or draw the Brillouin zone, and eventually in 3 dimension, your first Brillouin zone looks like this, and these are the 6 different points basically. Now, what is its implication? It has a tremendous implications. If you look at the energy band versus the density of states, because your band structure is like this, you can have a very small number of carriers at this point. So basically, you can have a very controlled experiment if you want to do, because of the carrier concentration, which is so small here compared to normal semiconductors. You can do a very, very controlled experiment. You can get modulated. For example, if you have an electric field, you can modulate basically, you can take the electrons here, or you can make the whole states here. In fact, this graph, if you see, this is a resistivity versus electric field, because this gate voltage is basically related to electric field. So you can modulate the charge carriers depending on what is the electric field. So you have electronic state, or you can have whole state, right? And those are very temperature dependent, electrical dependent. So basically, this is an ideal platform to do very, very controlled experiment, both electronic and whole state. But there are some serious problems. I'll talk about that. But one of the biggest challenges that even though you have high level of control of these carrier concentration, but at the same time, they're also very prone to the environment. So it's extremely sensitive. And in fact, in the early days, graphene was used as one of the most sensitive materials. In fact, till today, it is the most sensitive materials that can be used for monitoring the environment. And it was demonstrated that it can be used as a single atom sensor. So that's a huge field, but it needs extremely controlled experiment to make those type of devices. And I believe the devices I'm going to show today is one such device that it can be used for very, very sensitive signals. Now, if you do not have, typically if you take silicon dioxide and put a graphene on top of that and try to modulate the charge carriers by having 2 different electrodes, a source and drain, you can do that. But as I said, because it is no single atomic layer, it can be extremely sensitive to the environment. In this case, you have an oxide, and top of that you have graphene. And as you know, oxide has different types of trap states or interface states. And when you try to push an electron from this side to that side, obviously, if you have a bulk material, then you do not have much trouble, because the charge carriers have enough bulk material that they can flow inside. But when you thin the material into a single atomic layer, then your disturbance becomes huge. So as a result, the noise, so-called electronic noise, is also going to be huge. And that's exactly what we are working on now, to understand the noise and how we can reduce that, things like that. But another thing is that, so if you look at this contour plot, this red and the blue type, those are puddles. At this this Dirac point, you can also basically make a kind of a bound state of electrons and of holes. Those are called electron hole puddle, and people have actually imaged those type of states, electron hole puddles. Those are kind of islands. And it's very interesting if you try to understand, how is the transport at those kind of, near to the Fermi level or near to the Dirac point. What is the conduction? It's extremely different, compared to the normal electronic transport as we understand even from silicon device. So there are really a lot of differences even in the transport when you compare with say silicon transport in silicon device. Now, to give you an example, just to give you a flavor of what type of a device I'm talking about, is a transistor device, and probably some of you or many of you are very familiar with. But let me explain you from this simple diagram. So you have a silicon substrate, and then this is called so-called channel. In our case, this yellow one is graphene, and you have a gate. This gate can be a top gate, or you have an oxide here on the top of silicon dioxide, and then material. That's called a bottom gate. Now, in normal transistor, you have to dope it. If you have a p-type silicon, you have to dope it, n-type, n plus, a heavily doped, and heavily doped. So you have a p-n junction here, So you can control the channel by that way, and you have source and drain. But typically, when you have nanomaterials, you have a different types of type of transistor. You have silicon dioxide, you put the graphene, and then you put another metal here, source, another metal here, drain. So those are called as Schottky barrier transistors. Those are not typically like silicon transistors. Those are Schottky barrier transistors. While broadly they are transistors, their operation is different. But nonetheless, as you know, even in a p-n junction, you have a barrier, right? So think about, instead of you have a p-n junction, you have a Schottky barrier here, you have a Schottky barrier here, and in between, you have the channel. So basically, you control your charge flow through the Schottky barrier. So it's an extremely important factor when you make a device from graphene or 2D material. To control the Schottky barrier is one of the most important factors, and we spend a lot of time to control and understand those Schottky barrier. But if you look at a graphene transistor, typically, you measure the current in the drain. That's called drain current, and you apply the voltage here. It's called gate voltage. Now you see this is the highest, and this is the lowest current. There are a couple of differences compared to silicon, for example. Here you can see like this, and it's coming to a minimum, and it's going like this. So this side is called N channel, or electron conduction. Basically, the conduction this side is dominated by electrons, and this side by holes. So that's an advantage. This is called bipolar kind of devices. So you can actually have a p-n junction itself there. But the big disadvantage is that if you look at this in a current level, it's called on current, and this is off current. The ratio is only 2 or 3, something like that, right? So it's a very on and off ratio. So you cannot really make a computer chip from such a small on and off ratio. So that's still today, it remains one of the biggest disadvantages of a graphene device. People are trying a lot to improve it, and over the last 15-16 years, substantial changes have been made, and it is found that nano ribbons, graphene nano ribbons, they're the most promising as far as the CMOS application is concerned. But they have also other problems, which graphene itself doesn't have, is the high mobility. So if you take a graphene and make a transistor, your on-off ratio is low, but if you have a decent quality of device, or mobility will be very high. It will be much higher than best silicon transistor. So if you are looking for an application where mobility is a main parameter, then graphene is one of the best material. In fact, like communication RF type of devices, graphene has a lot of promise because those applications are primarily driven by the high mobility type of things. So practical GPAD has a lot of problems, but they have also a lot of opportunities, just like high mobility type of application. But even if it's a high mobility, as I mentioned in my previous slide, if you are trying to build a high mobility device, but extremely sensitive, then that's not enough, because still your carrier, they are going to scatter very intensely from these interface states. So how to deal with that? And that's where we are. Our focus is, we have two goals: how to make a high performance, ultra high performance, in fact, device with ultra high mobility, but at this time, how we can ensure that the device will have extremely low noise. So noise in electronic device is ubiquitous. Like you cannot eliminate it. You can reduce it, but if you're really a great device physicist, device engineer, you can probably substantially reduce it, but you cannot completely eliminate it. And that's because it has its physics, right? To understand, go to the bottom of this mechanism, and in fact, in graphene, the mechanism is completely different again, compared to silicon and things like that. And again, long story short, when you measure the noise, so-called noise, basically noise can come from either current or voltage, things like that. In our device, for example, you are measuring a drain current, so any fluctuation can be considered as a noise, right? So you so-called measure a noise spectrum density. It can be voltage noise spectrum density, or it can be current noise spectrum density. So you plot this in the y-axis, and in x-axis frequency. Now, if it is really if it is like this, your signal, then it can, as you can see, it fits well to a function 1 over f. That's why it's called 1 over f noise. But it's not necessarily always be 1 over f. It can be 1 over f to the power 1.5. It can be 1 over f to the power 2.5, depending on the material. Then you have to think about what is the physics behind it. Now, this noise amplitude, it can be, if you sum over all the frequency, for example. So this is just the formula of a noise amplitude. Now, the different thing in graphene is that it's a very confusing. Some people say that the noise becomes like M type. Some people, they say it becomes delta type, V type. So it's a very kind of fundamental research if you try to understand what happens to the carriers. So this is what was our very initial measurement, beautiful noise plot. One thing that you can see, this is from a single graphene layer transistor. You can see that you have this normalized noise amplitude, and this is your conductivity or your drain current. Wherever you have the lowest value of a drain current, you have the highest noise, and that's kind of very counterintuitive. You think that when you have higher current, you have more carriers and you'll have more noise. But in case of a graphene, it's the opposite. You have a low current, lowest the current, the highest the noise. And that's because of, as we are explaining in the Dirac point, you can you can have such control of the number of carriers, then completely the mechanism of noise is different. Now you can see there is an offset voltage from 0 to 30 volt. And that's primarily because graphene is sensitive. If it's not clean enough, it is very hard to get at a 0 data point. Of course, these are our initial results, but we have now a very good control that we can bring it to 0 at a data point, so that we can ensure that it's not p-type or it's not n-type, completely doped. Now this is bad. This can be also good. If you know how to manipulate, you can dope it either p-type or n-type. So again, it depends from what angle you are looking at, but if you can control it, you have the ability to change the charge carriers in graphene channel. Now, one of the great discovery in 2013 was by Lei Wang et al. At New York, Columbia. And what they did is a very smart way, like they put the contacts. Typically when you have transistor, you put the contact on graphene itself, right? So if you have a multi-layer graphene, only your top layer is contacted to the metal, but that way you may not necessarily kind of modulate all the charge carriers in all the layers. Now this is a so-called 1D contact because it's only on the edge, not on the top, right? So only the edge, if you have a two-dimensional material, the edge is kind of one-dimensional, right? So your contact is only contacting, or the metal is only contacting to the edge. So that's why it's called 1D contact. It's extremely hard to fabricate in this device, but it's doable. It's not impossible. So if you really can be an expert in the fabrication to make this one, then I'm pretty sure you can have very high mobility devices. But not only that, you can see this is graphene, but also it is so-called encapsulated by another 2D material called hexagonal boron nitride, that is very, very lattice matched with graphene, but it has, of course, boron and nitrogen instead of carbon. But the lattice constant, since it is similar, you can have so-called epitaxial layer. And as we know, if things become epitaxial, then you can substantially you can increase the mobility. Now that's what exactly happens. Now, if you can really make ultra clean and this kind of epitaxial layer with the 1D contacts, then you can have very high mobility. And this paper, first time, they showed that this configuration can give you very high mobility. Now that was not our focus, but we were able to make such kind of a very high quality device, but our intention is to understand the noise, electronic noise, and also how the noise and the transport, electrical transport, they are correlated, because you will not find many work where they really try to explain in a correlated way the transport and the noise, and that is our focus actually. So what we did, this is the device fabrication. You have a substrate, in this case hexagonal boron nitride, bottom layer. Then individually we have this graphene, and these are not very small. These are 10 15 microns. Sometimes we get 30 40 micron, and then you have another hexagonal boron nitride. So you have a technique, and it's widely used now in various groups, and then you stack them together. This is the whole stack, hexagonal boron nitride, graphene, and hexagonal boron nitride. It takes some efforts, but you'll be able to make it. Now you can see some of the bubbles inside. These are the air pockets, air bubbles, but we have a technique to push them out. And so that, because we have to make sure that this interface is very, very connected and high quality interface. Otherwise, you will not get high quality transport and also noise. So after that, this is the final device. You can see the various leads and source and drain you can use, and it has a back gate and where you can modulate the charge carriers. Now, if you cut it and look at the cross section, this looks like this. This is the schematic of the device. Now, of course, it is hard to see where the graphene is, but this one, you can a little bit more clearer. You can see these lines. These are hexagonal boron nitride. This is top hexagonal boron nitride, and in between, you have the graphene. If you do not believe from this TEM, then you have to believe from this Raman, where you see that you have a smaller G peak and a much higher 2D peak. That means it's single layer, and you have also hexagonal boron nitride peak is there. That means it has to be hexagonal boron nitride graphene, single layer graphene, and hexagonal boron nitride. Also, you can have elemental analysis where you can monitor each and every element. So now looking at the transport, so if you look at the transistor characteristics, actually it's a very nice bipolar. As I was saying before, this is your hole transport, this is your electron transport. So both electrons and holes you can generate depending on how you are controlling the electric field. Now we did also temperature dependent of this transport or conductivity. You can see very nice variation of this conductivity both in the hole region, in the electron region, and also near to the Dirac point. And if you extract the resistivity, you can see very nicely the resistivity is actually changing from p-type to n-type through the Dirac point. You can extract the mobility using this mobility formula, where this is your transconductance, and this is your oxide capacitance. BDS is how much is the drain voltage. This is the length of the device, width of the device. So if you extract that and plot your mobility, this is your resistivity. Mobility looks like this. Now look at how high is the mobility. So this is 80 K, and this is room temperature. Room temperature, almost electron side, we got more than 50,000. So 60,000 the mobility, 60,000 centimeters square per voltage second. So at room temperature itself, it's 50,000. So it's a very high compared to silicon. Now with the temperature, as you can see at 80 K, we got almost 140, 150,000 the mobility. So very, very high mobility. So that's how we kind of confirm that our devices are having ultra high mobility. So we ensure that before measuring the noise. Now, as I was saying, this is the noise spectrum, basically. So SI is the noise spectrum divided by current square. That's called normalized noise versus the frequency. As you can see with temperature, we measured all the noise at every temperature, and they all kind of look like, this is your 1/f trend. So primarily it looks like 1/f. But it's very interesting, if you look at this Dirac point and slope of this, as I was saying, if it is 1, then it is 1/f. You can see the slope is not always 1. Actually, it can vary from -1 is basically because it's decreasing, right? So if it is just 1/f, it will be a flat straight line. But look at this, at a Dirac point, you have lot of variation, And that's why, like, in the beginning, I told that, graphene is very, very interesting, very, very different, because you see a lot of interesting things around Dirac point. And this is really interesting. So when we extract so-called the noise amplitude versus the gate voltage with different temperature, as you can see, we can vary from this, depending on what temperature, we can vary this noise at the Dirac point, this lambda type to V type. So this is the first time we have systematic understanding of how noise changes at the Dirac point from lambda type to V type. And that was something really, really interesting. Now, to understand, how we can have a better knowledge about this origin of noise, we have a model. We derived a model. Basically, your noise amplitude is some factor, say alpha, which is a characteristic constant called whose constant or whose parameter divided by n. N is the number of carriers in the channel, and you can actually sum over all the frequencies, and that is basically frequency time your noise amplitude divided by the drain current square. So basically your alpha h over n equal to f times, which is frequency, times si over id square. Now this alpha should be a parameter that is should be a function of mobility and trap, because how much noise is depends on how mobile is the charge, but also what is the rate of generation of these traps in the interface. So we do not know what is the exact form, but we know that it should be a function of mobility and the trap states. And again, it's a very complex function, because your mobility depends on what is your electric field, what is the temperature, and trap state depends on what is the depth of the trap states from the oxide or interface, and what is the temperature. So it's a very complex function. But if we use like this, then we can write your noise amplitude is 1 over n, and this function, which is basically your alpha. But we know also mobility has a different origin. Mobility can be from different sources. For example, mobility can be from your intrinsic mobility, or it can be from long range scattering. This is a short range scattering. This is long range scattering. This is your longitudinal acoustic phonon, and this is something called a remote interfacial phonon. So these are the in case of graphene, these are the typical dominating factors that can change your mobility. So we must also consider that. So in principle, this mobility should be your effective mobility, which is again dependent on all these factors. So we did extensive measurements with temperature, this resistivity versus the temperature, and from which we calculated alpha, and also independently we calculated mobility, and we did see that they are very tightly correlated. So alpha and mu, you can see with temperature, they are very much correlated, and we have a functional dependence. If you can look at our paper, so we kind of find out some of the correlation between from this plot. Now, independently also, we extracted the so-called residual resistivity. So residual resistivity is basically your short range scattering, resistivity from the short range scattering and long range scattering together. We call it residual scattering. And you can see the residual scattering, at the Dirac point, goes extremely high. And that's where temperature helps us, because if you calculate the longitudinal acoustic phonon factor to the resistivity and remote interfacial phonon factor, then you can see that your this remote interfacial goes also very high. So depending on what temperature, you can actually take one of the factors, and eliminate the other factors, things like that. So to understand the trap states, let me see how much time I have. Okay, so to understand the trap states, now we also need to know how this trap energy, which is in delta E, is dependent on temperature. So we have a model that your trap states can be modulated with the temperature within this type of behavior. Typical behavior exponential minus energy divided by kT. So by taking that, we and again from our experimental data, this is your log alpha versus 1 over T. So we extracted actually the delta E, which is trap state energy, and this is first time we derived the trap states in this type of high mobility and ultra high mobility devices to be between 5 millielectron volt to 17, 18 millielectron volt, depending on you are in whole state or electron state, but nevertheless between 5 to 20 millielectron volts. So they are really, really small, but we are, by doing this fine experiment, we are able to extract this extremely small energy level of these trap states, and we truly believe that these are responsible for giving this ultra low noise. And we also depending on based on all this information, we extracted we model the band structure of our device. And so this is your transistor device with a 1D contact, source and drain, and this is your channel. And since we are modulating the charge carriers by gate voltage, when your gate voltage is just smaller than or negative, you have the band bending like this, and in that case your whole states are here. But when you have a positive gate voltage, that means you pull the channel so much, then you are generating your electronic states. Those are responsible for the transport. And of course, this is depending on what is the drain bias. This is the amount of energy level that you pull in the drain side, and accordingly your band structure of the channel becomes like this. Now you can think of with our extraction of these trap states between 5 millielectron volt to 20 millielectron volt, you can model it as when your transistor is operating in this regime, then you have enough whole states near to the conduction band or near to the Dirac point, but in the whole side, these are the states. Those are responsible for giving you the noise from the holes, and this can change with temperature. As you increase the temperature or decrease the temperature, you can populate accordingly those whole states. Whereas if you pull the band with a positive gate voltage, then you have electronic trap states above the Fermi level or above the Dirac point, but very close to the Dirac point. And you can also populate accordingly with playing with the temperature. And so this is, we believe this is the first time we have this precision level control of the noise. And in fact, our device is the lowest, having the lowest noise in graphene-based transistors. And in this case, of course, it's a special type of transistors, hexagonal boron nitride encapsulated and with 1D contact. With that, let me summarize my talk. Graphene may not be of material of choice for transistors for CMOS application yet, but continued efforts have been shown greatly over the years, ribbons being the most efficient for CMOS. However, GPETs are undoubtedly high mobility devices and have promise in communication applications. Ultra high mobility graphene transistors can be achieved with epitaxial graphene with hexagonal boron nitrides, and moreover, those are the configurations where you can not only ensure ultra high performance but also ultra low noise. With that, I would thank our sponsors for funding to do all this work. And of course, I thank a lot my group members without whom it's not possible to do this work. So thank you very much.
Thank you, Professor. Thank you for your talk. So it was a very informative talk about, you have briefly explained about carbon-based materials and as well as graphene-based high-performance two-dimension PET devices. So now I request the audience to interact with Professor Das.
Sure, thank you.
Nice presentation, Professor Das.
Thank you, thank you.
Audience, now I request audience to interact with Professor Das.
Excuse me, sir.
Yes, please.
Sir, I'm out of the material science. I don't know much, very good idea about the conductivity, but still your presentation made me curious about the conductivity or conductive properties of this graphene. So I was looking at the conductive polymers, how it conducts, like conjugate bonds, things and all. However, in the case of graphene, I don't think there is a conjugate bond.
No,
Usually polymers conducts in ionic conductivity or like that. And how conductive mechanism works in the case of graphene, I'm very curious about it. Please.
Yeah, so did you finish your question?
Yes, sir. Yes, sir.
Yeah, so as I was showing in my earlier earlier slides, primarily the conductivity is governed by drift diffusion type of in the semiconductor, but it's a single layer. So it's not exactly drift diffusion. Even if it's a drift diffusion, it's very different because it's just a single atomic layer, right? And more importantly, as I told in graphene, because of this conical band structure, the mechanism is very different. So this is why they're called so-called Dirac materials, because it's not just because of the conjugate polymer type, or it's just not just because of a van der Waals type. It's because of the special band structure, and special band structure governs the conductivity. So I would say graphene is altogether defines a different types of conductivity.
Thank you, sir.
Yeah, but interesting point you made, and actually a lot of people are working now to understand, like, how they can, for example, attach this type of special conducting molecule with the graphene, and what will be the transport in those type of things. Still not very clear, but that's an interesting area.
Thank you so much, sir.
Thank you.
Participant?
Yes, I have one more question. As I can see, the device has been encapsulated by hexagonal boron nitride. Mostly the lattice mismatching, as you told. So whether if we encapsulate with other materials, whether it will perform with the high mobility, or what will be the effect of the noise? on the noise?
It's very hard. It's very hard because from our solid state physics knowledge, we know that if there will be lattice mismatch, there will be a lot of problems, right? So I do not think that so far there is any material that will challenge hexagonal boron nitride. It's just because they are exactly similar, like almost similar type of lattice. Now if of course you can think of in hexagonal boron nitride you have boron and nitrogen. They're different from carbon, right? So if you can have if you can discover another material with similar lattice constant with the carbon, then of course that will beat boron nitride. But yeah, but boron nitride, coming to your question, boron nitride, they far material, best material for having this ultra high mobility graphene transistor.
Thank you.
Thank you.
Participant, anybody wants to ask any question? Okay. Right.
Sir, myself.
Yes, please.
Anna.
Good morning, sir. Sir, in my material, when I draw, I am doing it with polymers. When I did this coal plot, I get the trend. I get very beautiful graph, but instead
Sorry,
of
say it again. When you make a polymer,
I'm working in polymer material, sir, and I also did this dielectric measurements. And when I drew the coal plot, Z dash and that resistance Z dash and Z double dash, I get a beautiful curve. That graph and all, I got very pakka graph, but instead of conductivity increasing, the curve was shifting beyond, sir. I couldn't understand what was the reason behind it, and I didn't find any papers also like that. So can you please throw some light on it, sir?
So coal plot you are making, are you looking at the ionic conductivity or electronic?
Ionic conductivity, sir.
Ionic conductivity. I see. Well, that is very different from electronic. Typically, the results that I was showing, those are electronic conductivity, right? But if you are measuring coal plot, depending on how is your sample configuration, you can actually model it, with a resistance capacitance model. If you really want to understand that, and then do some controlled experiment to kind of identify what is your ionic conductivity versus what is interfacial resistance, things like that. Typically, people do that by modeling coal plot.
Okay.
Yeah.
Thank you, sir.
Thank you.
Participant, anybody wants to ask any question? Right. So there is no more question. On behalf of all the participants, once again, I thank to Professor Das for his valuable and informative talk. Thank you, Professor.
Thank you very much, and thank you everyone for this wonderful idea exchange. Thank you.
Thank you, Professor.
Bye. Take care.
Yeah, thank you.
Good morning, everyone. Thank you, Professor Das, for nice presentation. Now going forward from here, our next speaker, Professor Ravindra Pandey from Michigan Technology University, USA. And now I would like to request Dr. Jayalakshmi, Assistant Professor, SRMIST Ramapuram, to introduce our speaker to our audience. Ma'am.
Welcome, Ravindra Pandey, sir. Sir? Ravindra Pandey, sir.
Yes, namaskar.
Namaskar, sir.
Sir, am I audible?
Yes, please go ahead.
Yes. Sir.
Good evening.
Sir, can you open your video?
I think I did open.
Yes,
Yes. Ma'am, you please continue. Jayalakshmi ma'am.
As the middle of the night, it's just midnight, so that's why you have dark background.
So, welcome, Professor. Dear participants, I'm very happy to introduce Dr. Ravindra Pandey. Ravindra Pandey is a professor and chair of physics at Michigan Technological University, Hong Kong. Professor Pandey received his education at Hari Singh Gaur University, Sahar, National Physics Laboratory, Delhi, Atomic Energy Research Laboratory, Harvard, UK, and University of Manitoba, Winnipeg, Canada. He has participated in multidisciplinary efforts to build the programs in novel nanostructures and applications of chalcopyrite semiconductors as the next generation optoelectronic materials with the industrial and national laboratories. He also has co-organized and participated in several international conferences in material physics and nanosciences. Pandey is a fellow of American Physics Society. Sir, we are happy to welcome you for this international conference, sir.
Thank you, Dr. Jayalakshmi. And I really rather admire persuasion of Dr. Jayalakshmi. She has been after me to give a talk in this conference. And typically, you know, I do not give talk at midnight, but I think it is for her and for the organizers, including Dr. Rani and others. So thanks again for giving the opportunity to share some of the results. Like earlier speaker, Dr. Das talked about the experimental component of graphene-based devices. But in this talk, I'll switch the gear. I'll definitely introduce you to concept of nanomaterials, but try to give some of the examples about how can we use the computational modeling to understand the properties of these nanomaterials. So can I go ahead and share my screen?
Yes, Professor.
So is okay now?
Yes.
Yeah, good. So let's proceed, and I'll take about 35 to 40 minutes to wrap up this talk. So I start with some of the experimental sort of results about the synthesis characterization of these nanomaterials, and then I'll switch gear to take you to my field, which is a simulation of these materials using a first principles method. So as Dr. Jayalakshmi said, I come from Michigan Tech, and you can see this is the northern part of Michigan. Detroit is somewhere here, this is Chicago, and we are up close to Lake Superior. There's a noise coming out, I think. Can you ask is okay now?
Yes, Professor, we will. Yeah. Yes, Professor, 1 minute.
Good. So this is because of the, again, Lake Superior, we have a beautiful campus. You can see.
Sir, excuse me, sir. You have muted.
Professor, can you unmute, Professor?
Yeah, it's okay now.
Professor, can you unmute and talk?
Is okay now?
Yes.
Good.
But we missed 1 or 2 minutes.
That's okay. Please add this thing. So I just talking about where Michigan Tech is located is I can get my laser pointer back again. This part of the peninsula, and because of next to the lake is a beautiful campus in summers. But what happens in the winter is because of the lake, it sort of dumps a lot of snow on ground. and the students for fun make snow statues. So just to give you an idea is, although you're in Chennai enjoying the summer weather, but still we have a winter up here. Temperature is about 5 to 6 degrees. So let's move on to my work, which I've been doing at Michigan Tech. Is the approach is the modeling approach, where we have is called quantum cluster or periodic supercell models, and we use either Hartree-Fock or a density functional theory, a Hamiltonian, to look into the properties of different materials. So I started my career back in days about looking at the bulk crystals, and then moved to clusters, especially the finite size clusters, and look at the quantum confinement effects, then nanostructures, and then 2D materials. But the current interest of our group is looking into the properties of this called a nano-bio world, where we have the biomolecules interacting with nanomaterials. And I'll give you some of the examples of this work. So as we know, nanoscience and nanotechnology has come up is a wonderful interdisciplinary field where you can combine the sort of pillars of the basic sciences with engineering. And if you look at the applications coming from the material science to information technology in terms of the devices, which a previous speaker has talked about it, and then some of the applications are in medicine or also in biotechnology. So I'll focus on sort of a physics and chemistry of the materials, and then look into this sensing property, which can be applicable to biotechnology or medicine area. So the background is, I'll give you, since we have about 40 minutes, I'll skip the so-called the fullerenes. And then the previous speaker has talked about graphene. So simply in this talk, I'll talk about the carbon nanotubes. And he also alluded about the boron nitride monolayer. So I'll look into some of the results on the boron nitride nanotubes, which are structurally similar materials, but electronically totally different, dissimilar materials. And then take you to this nanobio world using the approaches in the modeling. My message is going to be the future is definitely is going to be when we bridge the gap between this biological world and sort of the nanotechnology in two different sort of aspects. So this is a sort of a slide which you may have seen previously. What we have is that this is a man-made world, and on top is a natural world. And if you look at the length scale, is the top of the pin is about 1 millimeter, and we have an ant about a few millimeter size all in length. And as we further go down, we have a DNA molecule, which is about in a nanometer diameter. And really what we have is here, the other right-hand corner and down up here is the gold sort of a 46 atom cluster, which you can definitely see through the imaging techniques. So that's definitely is a one-to-one relationship between what we call man-made world related to natural world. So what's so good about nanomaterials is, and I think is really credit goes to experimentalists, because what has happened in the last about 10 to 15 years, the tremendous advances in imaging techniques. And because of it, in a sense, we can really see the surface topography at the atomic level. We can really count atom by atom. And especially these two approaches, which we have is the AFM, is atomic force microscopy, where we can do the 3D magnification, which does provide a very, very high contrast. And we can definitely look into the morphology or physical properties of the material. If you go to other hand is SEM, what we have is a 2D magnification. And because of it, we have a high depth of field, which definitely provides the information about the chemical composition of the material. So these are the two major tools which has helped us to move towards this nanomaterials or nanotechnology area. And here is one of the AF image where one is looking at is the gold clusters. And you can see definitely you can count in about the size of nanometer, these clusters sitting on a silicon carbide substrate. So this is again is a cartoon which tells you is how we connect the so-called imaging techniques with the tools we have available in the computational world. So if you look at the macro, is they're talking about the length scale, and this is the time scale. So on this hand, we have optical microscopy is available, and what we have the tools in terms of either the continuum models or what we have the discrete dislocation dynamics, which we can look into the surface structures. But as we go further down here, you can see here is a high resolution TEM or SEM-TEM. We are talking about nanometer in length, and of course is in about a second to microsecond in time scale. And the tools which we have available are based on is the quantum mechanical models, or we call the atomistic models, both MD and DFT. So this sort of image gives you is if you look into the STM, where graphene is sort of deposited on the silicon carbide at a certain bias, you can really visualize the monolayer of graphene, where you have the nice hexagon formed by the carbon rings. And if you go further down here is you have the bilayer, and you can characterize it by looking at the conductivity, the derivative of current with respect to voltage. And you can see nicely this is the sort of represents the monolayer, and this curve represents the bilayer of graphene. So you can really distinguish between a monolayer to bilayer and further multi-layer compounds using these beautiful imaging techniques. So what is sort of special about nanomaterials? And you may have seen again this slide, but again this sort of gives you the power sort of conceptually. That if you look at the cube and you calculate the surface area, so it's a centimeter by centimeter cube, and surface area is going to be about 6 centimeters square, because you have again is a 4 plus 2 up and down 6 surfaces. If you go further down, instead of a centimeter cube, we pick up a millimeter cube. We subdivide it, and we find is definitely surface area has gone at least 10 times. Going from centimeter to millimeter, the surface area increased by 10 times, going from 6 centimeters square to now 60 centimeter inverse. But going from this millimeter size cube to, if you go to a nanometer size cube, and look at the advantage, what we have is a significant increase in surface area. So nanomaterials, the sensitivity or reactivity or applicability, definitely it comes down to is available surface area at the nanoscale in terms of what we have in the macro scale. And that's why these materials have been now sort of used for the next generation devices or applications. So the key thing is surface area. So this is again, it tells you is as we shrink the size of these nanomaterials, what happens in terms of the quantum mechanics. So I call is the quantum mechanics 101. So condition what we have is the diameter of this quantum dot is very, very small compared to what we have the de Broglie wavelength. So if I pick up a gallium arsenide, about 500 atom clusters, so what is happening here is if you look at on top is we have the discrete atomic energy levels, again you can see here, with a certain gap between these two states. But as we bring in these atoms together, what we have is we form a sort of energy bands, and because of this energy well, it sort of shrinks the gap, and energy level sort of increases. So this is what we call is a quantum confinement effect. So what it does is we have now a tool to sort of manipulate or exploit the size dependence properties of these quantum dots. And by varying the size, you can sort of vary the HOMO-LUMO gap or the sort of a spectrum of the absorption and emission of a given system. So how we classify these materials, and when you talk about quantum confinement, so what we have is you may have seen is the 2D material or 0D quantum dot. So it comes down to the classification based on what we call is a spatial confinement of the excitons, which is our carriers, electron hole pairs, in one or more dimensions within a material. So in a sense, what we have is a 3D material, means our carriers, which are the free carriers, can definitely move into 3 directions. If you go down to restrict the movement on a plane, then we have the 2D materials. If you come down to sort of only the one direction, this could be the axial direction, like a carbon nanotube, then we have the 1D materials. And of course, if we confine in all directions, we have so-called the quantum dots. So we use the confinement of these electron hole pairs as a basis to classify these materials. So what happens in terms of the energy levels, which we talked about, is that we have quantum confinement effects. So you can see here, again, this is a cartoon here, is we have the availability of the carriers and how they're distributed in terms of what we call density of states. And that's a very common concept in solid state physics, which means what we have is number of electron states per unit volume, per unit energy. So for the bulk system, in terms of the quantum confinement, what we call 3D confinements, but you can see we have nice continuous distribution of density of states. There is a cutoff at a certain point. But if you go to 2D points, it is further more restricted. Coming to 1D, it's really confined. And then you can see the 0D is simply the discrete energy levels. You can see here in terms of as we confine the movements from 3D to 0D, the restriction in terms of the energy distribution of carrier occurs in terms of the physics of the system. And that's why one has to be aware of this restriction if you're looking into the properties of this application of these materials for different devices. So for carbon-based nanomaterials, now we can definitely talk about 3D as a bulk like a graphite. We can go to 1D, the carbon nanotube. We have the fullerenes, which are the quantum dot, 0D. And then we have graphene, which is about a 2D system. So what is so special about these carbon-based materials is going from graphite to fullerene. So this is again is a chemistry 101 I call the bonding slide. Is these carbon atoms as really, if you see the 4 valence electrons, the sort of going to the 2s, and we have the 1 each on a 2p orbital. So if you look at the sort of s orbital, and then we have px, pv, py, and pz orbitals, you can see the hybridization of sp, because we have these 4 orbitals in a carbon system. The sp hybridization gives a sort of a linear chain. sp2 hybridization gives you, again, is with some angle, the planar structure. And then we have the sp3 hybridization, which sort of introduces the bulk-like structure, which we can see here. The carbines are sort of a linear chain of carbon molecules are in sp type. sp2 type is again is sort of a graphene mixture is a nanotubes, and then sp3 types is indeed a diamond and part of the fullerenes. So this flexibility of these electronic sharing in between carbon atoms really yields a variety of different structures. So this is again is the cartoon is the carbon nanotube, and most of us know is that depending on if we take the plane of the paper, and depending on how we roll the paper, we can have the zigzag type of carbon nanotube or a armchair carbon nanotube, when in between we have the carbon nanotube. And interestingly, depending on the way we fold these nanotubes, it can be either metallic or semiconductor. So that's the difference depending on the direction. So this is again is just to give you an idea about the CVD method, which is commonly used to grow these nanotubes. This is sort of, we have the organic membrane. And what you do is using the precursor at 18 degrees Celsius, simply deposit, and what you have is a nice bundles of these carbon nanotubes within these oxide pores. This is a quite a common approach to see it. Now I just would like to feel I call is about the idea is when we talk about the 1 micron long single walled carbon nanotube, and look at the mass or the weight is about 10 power minus 18 gram. So what you're looking at, if we talk about the 1 milligram of carbon nanotube, we have really 10 power 14 pieces of these carbon nanotubes. So you have to think about really is a very, very small quantity. It means we have large number of these carbon nanotube bundles are in the system. And if I look at the 1 centimeter square area, and with some defined spacing for a given device, we had to have about 10 power 12 the pieces of single walled carbon nanotube. So this sort of gives an idea is going from lab scale to I call the manufacturing scale. One has to be very, very careful in providing such a large quantity of nanotubes without any defects. And that's a sort of a challenge which industry is facing. How do we know is how good these nanotubes are? And the typical thing is what we have is called Raman spectra. And this sort of slide tells you is what we are looking at the strength of this bond between carbon in a given material by vibrational modes, because these systems are at the room temperature. The bonds are going to vibrate. And in terms of the quantum mechanics, each bond, what we call, is sort of corresponds to a potential well where the molecule lies. From there, what you can do is you can really determine the so-called the Raman active mode, which is directly related to the polarization, the flexibility of the electronic cloud in the system. So if we have the so-called the unpolarized electronic cloud, and it becomes a sort of polarized in an external field, and then what we have is this sort of a transition provides so-called the Raman active mode for a given system. And for the carbon nanotubes, that's sort of we call the G band is about 1592 centimeter inverse. So both the location and the height of this band sort of tells you that how good your carbon nanotubes you have grown in the system. So that's a sort of a quality check for the given sample. So let's move to graphene, and I think let me skip this thing because it has been talked about by previous speaker. And let me go into the applications. So we have again is these nanomaterials have been used or proposed for energy applications, especially in terms of the solar cells. And as you know, the solar cell basically is defined by a conversion of photon coming into striking on the cell, which it generates these electron hole pairs. And then we apply the bias, electron goes to cathode and hole goes to anode, and then the current is flowed. So the advantage of graphene or carbon nanotube or carbon-based material is the mobility. But they have again certain challenges which can be sort of addressed in different talk. The biomedicine also is proposed as a drug carrier for these carbon nanotubes. But I'll look into sort of a sensing part of these nanomaterials. So this is again is a cartoon, and which we have worked extensively in looking at the so-called DNA functionalized carbon nanotube. So as we know is a carbon, especially in the plane, if you look at the sort of a curved nanotube surface, tubular surface, we have so-called the px, py orbitals are bonded in plane, but the pz orbital is floating around. And what happens is it forms what we call is the pi electron cloud. So in order to, again, make the sort of these carbon nanotubes active in terms of the sensing, what it does you have to functionalize it. And the best way is to do sort of a DNA, because the DNA, as if you remember, has about 4 nucleotide bases, guanine, adenine, thymine, and uracil. Uracil is and cytosine. So these ones are nothing but carbon rings. And so these have, again, the pi electrons sort of available for interaction. So this pi-pi interaction gives you van der Waals bonding between a DNA, a molecule, and carbon nanotube. So DNA becomes a sort of a probe, and then you have the target coming in and sort of, I think, making sure you can sort of have the sensing properties. So what you do is you have this cartoon. DNA is sort of functionalized the DNA. Carbon nanotubes functionalize the DNA is our sample. We have source and drain, and this is our gate field, applying the gate. So if I look at the conductivity versus the gate voltage, I can see the bare nanotube has a certain characteristics in black. If I functionalize the DNA, I call the probe, which is in orange, has again a distinct characteristics in terms of conductivity, gate voltage curve. And if I bring in my target, which is attached to the probe, you can see here distinctly the green part is nothing but the hybrid material, which we have the target, probe, and a carbon nanotube. So by changing the shift in the signal, going from pristine to target to a probe, functionalized, and then the hybrid, one can sort of distinguish the sensing capability or the identity of that molecule which are being sensed. And this again is the ppm level sensing is now again can be done, and response and recovery is definitely in seconds. So question comes down to now is, do you want to definitely you make this device, but you would like to improve the performance, and this performance can only be improved when you look at the what kind of interaction occurring at the interface. And in this sense, the modeling sort of kicks in and provides the understanding and interpretation of these experimental results. So our aim now is to provide a guidance to these device physicists so that they can improve the device performance from the fundamental understanding of the physics and chemistry of the interface. So we come in now is we do the modeling part, and let me show you some of the slides is what exactly the aim or motivation is. So we start with the hypothesis is the modeling definitely needs to provide the quantitative results of accuracy, not the qualitative, but quantitative results. And of course, accuracy and reliability, so that they can be used to predict the physical and chemical properties of materials. And this capacity is of course, visible in 2 grounds. First thing is whatever the model you choose, you have to first see how good the model elements are. So you compare your calculated results with the experiment results. And once you have the confidence that your model elements do represent the physical reality of the materials, then you can go on and sort of predict the properties which are either inaccessible or very, very expensive to resolve in terms of the experiments. The tools, what we have in our disposal is, you can see this slide. This is the length scale, and this is the time scale. And if I go from top to down, you can see this is a sort of the area in terms of the years or hours or meters, what we're looking at the finite element analysis or engineering design. But if you go further down, which is this area in terms of the nanometer or a nanosecond, you can see what we have, the tools available based on quantum mechanics or molecular mechanics. And what it does is they really provide a very, very accurate description of the chemical reactions and the spectroscopy, and also the structure, density, and diffusion in these materials. So this is a slide I'd always sort of show in my talk, is to give you an idea is when we talk about this electron phonon optic interaction, what kind of length scale we are looking into it. And as you see here is electronic transport, means what we are talking about is a Fermi wavelength or a scattering length. So this is indeed is in nanometer sort of a length scale. We go to thermal transport. And if you look at the phonon mean free path at a room temperature, this is again is order of a nanometer. We go to optical interaction where photon is interacting with your solid. What we have is again is the wavelength again is a few hundred nanometers. But when it comes down to magnetic interactions, when we are looking at again the interaction between say electron or dipole, we have again is the length scale in terms of the electron is about nanometer. But if you look at the dipole interaction, it does have a larger sort of a range in micron. So these electronic, thermal, optical, and electron magnetic interaction, they do come into the so-called the quantum regime of the physics. So in our group, we use this standard sort of now is technique is called density function theory. And what it does is it sort of takes the electron density of a given system and says that once you know the electron density system, you can easily calculate the ground state of energy. So that's the relationship between the energy and the electron density of the system. And it's sort of embedded in so-called the Korn-Sham equations. And you can see here, this is our Korn-Sham equation is nothing but is like a Schrodinger equation where we have H psi is equal to E psi. And H is the Hamiltonian, which sort of comes down to the kinetic energy term. And then we have so-called the exchange potential. This comes down to the Coulomb potential, 1 over R minus R prime term. And this is called exchange correlation energy. So we have these 4 terms, and knowing these terms is and the electron density of the system, which is square of the wave function, you can definitely calculate the properties of a given material. So this sort of gives you the cartoon is what kind of approximations are involved in solving this Korn-Sham equation. So if I look at the real system, is composed of the so-called electrons and our nuclei. So what we do is we start with the so-called Born-Oppenheimer approximation. What we say is in a sense we decouple electronic motion with nuclei motion. And the reason is, again, it makes sense because electrons are very, very light and they move much faster than the nuclei, and you can decouple their motions. So it becomes a so-called the non-interacting system. And from here, you can write these equations and you are trying to solve the equation in this so-called the effective potential. And effective potential, like I showed in earlier slide, is our Coulombic potential and so-called the exchange correlation potential. The trick of the trade in DFT, what I call is how to approximate this exchange correlation energy. And the exact form of this energy is not known. So what we have done is, rather a lot of people have done is they have calculated these functional forms in say called free electron gas. And from there, they approximated this EXE to do it. So what we do is our aim is to find out what is the ground state of the system. So you start with a sort of initial guess of electron density. And then from there, you calculate the effective potential. From there is you solve the Kohn-Sham equation. And you go back and you evaluate the electron density. And what happens is here, this is the iterative process. So what you find is if the calculated electron density, how different it is from the initial guess. And if this difference is very, very small, then we say is our calculation is converged. And then from there, we have so-called the ground state electron density and the ground state energy. And once you have the ground state energy and electron density, you can calculate any property of the system. That's the key thing here, to how to get this ground state. And it all depends on your educated guess. So this sort of tells you just an idea about how accurate these calculations are. So here we are looking at these carbon nanotubes. You can see here, and this is our one of the nuclei bases of DNA, guanine. So you can see here, this is a hexagon rings, and we have again the carbon rings in guanine. And really the interaction between these two, the governed by the van der Waals interactions, because these pi electron clouds coming from CNT and from these carbon rings interactive weakly, not very strong, but weak interaction. And then what we have is, if you look at the energy surface, we easily can calculate is about the 1/100th of electron volt between the 2 points. So calculations are nowadays is very, very accurate and reliable, but it takes time depending on what you would like to do. So that sort of gives you an idea how great these calculations are. So let's look at one of the examples. How can we assist experimentalists to understand what is going on in their experiments? So he's one of our colleagues, Dr. Sabir Hussain at the Air Force Lab. He came up and showed me this slide. So he's looking at the effect of nanoparticles in environment. I'll take another 5-6 minutes to wrap it up. So as we know, is the dopamine is a sort of one of the molecule which you can see the carbon rings with oxygen and an amine acid thing. And he's looking at the so-called the PC12 cells. So when he attaches the manganese nanoparticle of the different two sources, he finds that with time, the level of dopamine goes down. But if he adds the silver nanoparticle, that there is a decrease in dopamine level, but not as significant as you can see in terms of the manganese nanoparticles. So it comes out is experiments suggest us that manganese nanoparticle depletes the dopamine level in this PC12 cells. So he asked the question is, can we find out why? What exactly is happening? And it has again is a sort of application in terms of the toxic effects of these nanoparticles and in a big picture. So we thought, okay, let's start the question, and we look at the so-called the nature of the interaction of these nanoparticles with the molecule, because we got to start from somewhere. And so we take these nanoparticles and see if we can calculate the energy surface when they're forming the complex. So we have the manganese 13 nanoparticles, and we picked up 13 atom cluster because it's symmetric, it has an icosahedral symmetry. So that's the advantage in our calculations. And the symmetric depends on the degree of symmetry. The more symmetric the system is going to be the faster the calculation. So we picked up, as we know, is magnesium D5 4s2 electron system. And then we looked into silver 13. which is again is a D10 4s1 electron system. And as people do in experiments, you have to have what you call the reference case. If we have the D electron system, manganese, the S electron system, silver, so why don't we also take the P electron system, which we have is the Al13. So whole our idea is if you look at these S, P, and D electron system and see if you can find any difference in terms of the physics and chemistry at the interface. And from there, we can talk about why do these manganese deplete level of dopamine related to silver or aluminum. So the calculation is what we do is this is a dopamine molecule, and this is our sort of quantum dot or nanoparticle. And what we try to do is, because this nanoparticle can come and interact with this the surface, the hollow surface, the middle of the ring, the carbon ring at site A, it can go to site nitrogen site amino acid, which is this is here, and site, and then it can either go to the O site between those things. So we bring in these nanoparticles to different sites and calculate the energy levels at each point. That's the sort of animation. And what we have is this is called energy versus distance curve, energy surface. And you can see here is the top side, sort of starts from way far away. There's no interaction. There is sort of energy goes down. That's a sort of a ground state. And as we go further close to each other, the so-called Pauli's repulsion takes over and energy rises. So from these three curves, you can see is the top site has a lower energy compared to N site and O site. Means indeed, this Mn13 nanoparticle prefers to bind dopamine at the top site. That sort of a solution comes out. From there, you can calculate the binding energy of these Mn13 with the dopamine is comes out about a 1 eV for manganese 13. Silver, you can see is a big difference. Is the order of magnitude lower than what we have for manganese, and aluminum simply not bound at all. It doesn't like the dopamine molecule. So if you look at the so-called the charge density at the interface, and you can clearly see this overlap of electron density, what we call is orbital hybridization, is really preferred for this D-type manganese 13. And we have, again, is a dopamine carbon ring on the top side. So we have the pi electrons sitting on top. So PD hybridization is definitely preferred over silver is a S-type, SP, or of course PP, as we know from chemistry 101, they don't like each other. So it comes down to the effectiveness of nanoparticle interacting with a biomolecule is what kind of bonding they're going to form at the interface. So that's the thing is PD hybridization is going to be preferred over SP or PP. And definitely it sort of tells us is once these manganese nanoparticle interact strongly with the dopamine, they form a very, very stable complex. And if the complex is formed, then definitely we are not going to see the individual dopamine level in the system. So sort of this gives you a sort of a glimpse of what can be done. And then we looked into a lot of different systems, both the DNA and also the proteins, because the challenge is going to be in future. As we know, the sizes of these devices, look at your mobile phone, is getting smaller and smaller. And the question now is what happens if it breaks, it falls down and breaks, and the nanoparticle, the magnetic nanoparticle which are sort of formed this device, it breaks and comes down to in the environment. And you're going to inhale it, then is going to be any effect either with the DNA or with the protein. So that's we had done in terms of all these quantum dots and nanoparticles and carbon nanotubes. And what we came out again in terms of the fundamental understanding is if you look at the metallic CNT, the interaction between these two carbon nanotube and DNA is going to be a dipole-dipole-like interaction because of the flexibility of the electronic cloud coming from nanotube and DNA molecules. And what we call is a VDW, a van der Waals type, which is very, very weak. As you switch to boron nitride nanotube, which is semiconducting, and as we know, as a previous speaker also talked about, boron nitrogen bond is going to be semi-ionic compared to carbon-carbon bond. So you expect the bonding to be too different. And what we also have for boron nitride, which you can see, because the semi-ionic bonding nature, the electronic cloud is not flexible enough, like we have for CNT. So they have more or less sort of a covalent type, or what we call the polar pi interaction in the boron nitride case. So you can really go down system by system and look into in detail sort of the nature of the bonding. And because of this, then the response to different external fields in terms of either electronic devices, optical devices, or in terms of the biotechnology, sensing devices. So I hope I have given you a sort of an idea that simulation and theory really can provide you the fundamental understanding of the molecular interactions. And once we understand them, we can easily sort of look into the electronic, optical, or magnetic response for various applications. So just the last slide, just to give you an idea what has happened in the last 40 years. When I was doing a PhD, I was looking at the oxygen vacancy defect in magnesium oxide. We wrote a program which is very long. It was 50,000 lines. It took about 5 years to do it. And I was looking at the hyperfine constant, which is basically the interaction between electron with the nuclei in this defect side. So when I did everything, I found that my sign is right, but magnitude was totally wrong. And my advisor said, well, that's fine. This is your thesis, you have your degree. And now what we can do is we can calculate the same thing in about 10 minutes and within the 1% of the accuracy. So I think especially the young generation is really fortunate enough to have access to such a computational power, where if they want to get into this modeling field, they can easily get into and do a lot of sort of calculations to understand what is going on rather than doing experiments. So again, let me thank again to Dr. Jayalakshmi for her persuasion and really is asking me to come in and give it this talk. So thanks again to organizers. And we always thank our students, postdocs and colleagues over the years, which I've been fortunate enough to have it. So thanks again, and I'm open to any questions. Questions?
Dear participants, you can interact with Professor Pandya. If you are having any question, please raise your hand, or you can unmute yourself and ask a question.
No questions. Typically, I take it as everyone is sleeping or is very bored talk, is very bored. They couldn't understand anything.
Not at all, sir.
Not at all, sir. It is a very interesting topic what you have taken, because you have taken DFT and you have touched Kohn-Sham equations, everything you have explained it. It is really a nice explanation, sir. And that too, you have taken about the carbon nanotubes, the sensors, how it is working, and the gold particles, attraction of gold particles, how that sensor is working.
That's a very interesting topic. And as you know, is most of us back in India, we do experiments. But I've been trying to push a lot of groups to look into the modeling part. And these calculations can be done on a simple desktop, even laptop.
I am having one question. Though
please.
you are a theoretician, but I would like to ask one simple question. Have you ever simulate that if we take two probe for the measurement or this device, 3 probe measurement?
Yes.
So what difference exactly? Yeah.
What exactly is, so approach is, as you know, is when you simulate a device. I have not talked about it. We have done a lot of calculation called electron transport calculation, because I realized the previous speaker is going to give us an experimental part on devices. So I have not done that. I thought, let me change the subject. So what you do is you have these, the electronic densities. So you have the channel material, which you want to study, and you have source and drain.
Yes.
And we know is this is what we call the quantum region, and source and drain is semi-classical. So we use this electron density, and then we use the non-equilibrium Green's function approach to really calculate the current versus voltage device. So this, you can have the 2 probe measurements, you can see, look into it. Or what we can do here, we can take our material and bring in the STM probe, which is simple metallic probe. And what you do is simply the flowing current is overlap of electronic density for the tip and your system. And from there, you can really map out the topography in terms of the STM setup. And these are very simple calculations. Once you have the electron density, you can go to source, drain, gate device, or STM kind of topography.
Nice, Professor. Actually, I got the idea now to do nano in DFT just because of you only. I came to a conclusion that I can do nano in this DFT.
That would be great, and especially, and I can connect you. Yeah, go ahead.
Yes,
go ahead.
Professor. So still
I can connect you to a lot of groups in Chennai. One of our students is Dr. Pushpa is in Hindustan University. She does a lot of DFT. And if we can offer I typically come to India and offer a lot of local modeling workshops. And if I do it, I'll let you know. So you can come and definitely attend it. But it takes time. And the best part is find a good student.
Yeah.
And from there, we can learn. We always learn from students.
Yes. Yesterday, Kanchana ma'am also said hi to you, Professor.
Oh, thank you.
I conveyed your message to her. She felt very happy.
She's a good person.
Yes.
Any questions from students or participants?
Yes.
The young generation?
Our HOD ma'am mic is not working, it seems, Professor. She said it was very good talk and she thanked you, Professor.
Thank you. Good. So have a good night or good morning, all of you. And we'll be in touch, Dr. Jayalakshmi, and all the best.
Thank you, Professor. If no questions, now I thank our Professor Ravindra Pandey, sir. Thank you, sir. Thank you so much. Yes.
Dear participants, please be in the meeting. The oral presentation will be started here. Just please be in the meeting.
இப்ப கரெக்ட் ஆயிடுச்சு. ஓகே, கோ-ஹோஸ்ட் கொடுத்துருங்க.
So oral participation is here. Goni Rajendran sir. So the participant for oral presentation. Any oral presentation participant is here?
Goni Rajan sir, now you can unmute and you can start. Goni Rajan sir, we have given the co-host privilege to you. You can.
Okay, thank you.
Okay, fine. Now you may start and you can share your screen.
So I can't able to. Okay, sorry.
See, if you see the bottom, there is a option share screen.
Okay,
Just
so that's yeah.
you can click and
Share
select
document. Okay. Documents. And document is. Oh, it is unable to open. Okay. Please select. Okay, sorry, it should be in PDF format. Okay, just 2 minutes. I will have to convert into PDF.
No problem, no problem. PDF is
It
you
is
can
only
also.
PowerPoint presentation. PowerPoint.
Yeah, it's not supporting the PowerPoint.
No video, PowerPoint only.
No, ma'am.
Yeah, is it
Sir
okay
is
now, sir?
having the PDF format. That's what he is asking. He's asking. Sir, do you have a PPT format?
I have PPT, but phone is not supporting, sir. That was
You are presenting through phone. Huh?
yeah, mobile also. Yesterday I tried mobile also. I'm facing some problems. Oh. Export to PDF. Let's see. Okay, sir. Yeah. Okay. Okay.
Sir, Goni Rajan sir, no problem. You have the PPT in the PDF format. Now you can open the PDF
Yes.
and you can give the talk, sir.
Yes, sir. That
Yeah. Make it fast, sir.
Is it fine? Is it okay, sir? Can you able?
Yeah. Now. Okay. Fine. You may start.
Yeah. Good morning, all of you. I'm Gone Rajendra, presently working as assistant professor in Sri Chaitanya Institute of Technological Sciences, Karimnagar. So it is a part of my PhD work done in IIT Guwahati. So the topic of this today presentation is superior visible light photocatalytic activity from graphene quantum dots and TiO2 nano heterostructure for environmental applications. So these are my outline. First, I will just introduce why the hybrid nanostructure and what is the motivation behind choosing this work. And further, I go to the experimental section, how we prepare the samples, and then I go to the results, the different characterization tools, and then finally I conclude my results. So this is the introduction part where anodized is a well-known photocatalyst for long, having very active material for environmental pollution degradation of dyes. So anodized is better one as compared to the different forms of TiO2 as rutile and B-phase and different forms of TiO2. And this is advantage as compared to the other TiO2, that is a relative non-toxicity and low-cost material. And you know that these are the wide band gap material, TiO2 and zinc oxide, those are wide band gap. That is band gap is falls in the 3 to 3.5 electron volts. So the anodized band gap bulk material is 3.2 electron volt. And there are some problem with the bulk material where even it has the high free charge carriers, but the recombination rate is very high and the band gap is falling in the UV region. So we have to mold the band gap toward this visible region in order to achieve the visible light photocatalytic application, that is the solar light, right? So we know that why the hybrid nanostructure is very important, because to mold the band gap toward this visible region, we made the hybrid nanostructure. And what is the utilization of this hybrid nanostructure? One is that it can utilize the solar light, which is having 3 to 5% of UV light and 44% of visible light. So most of the visible light we can utilize by solar, right? So there are one more advantage that is making the hybrid nanostructure, that is high efficient charge transfer. That means if you use single material, so there is high recombination rate will occur. So that means we can the charge can be transferred from one metal to another metal if you make the hybrids. So there is one more another important that is charge carrier separation, right? So when the charge carriers are recombined, before recombination we have to separate in order to get the free radical reactions, right? So I have chosen the graphene quantum dots, one of the promising material which is derived from the graphene bulk material, I mean the graphene material. So this is the synthesis part. The top one is showing the GQDS synthesis. So where I have used the precursor materials. I have not shown the graphite flakes as a precursor for graphene oxide. So I have used the graphene oxide derived from the graphite flakes. So then graphene oxide is oxidized with sonicated with dimethyl formate solvent and with some 1 hour time. Then I did the chemical reaction under autoclave, dimethyl formate graphene oxide solution with 200 degrees centigrade for 7 hours. And I have obtained the graphene quantum dots with the different functional groups. You can see the edge defects. So we have also prepared the graphene quantum dots with different solvents like water and dimethyl sulfoxide. The results are not provided here. So we for comparison we have prepared 7 hours. Only I have used the DMF solvent and graphene oxide precursor material. Though the insert in the black color, the beaker in the solution is showing the graphene quantum dots in the liquid form. So in the next, I have prepared the TiO2 material by using the simple ball milling technique, so that the size of the TiO2 nanoparticles is reduced by ball milling process. Right. The next one, I have prepared the hybrid nanostructure of graphene quantum dots and TiO2 with a simple ultrasonication, and after that the centrifugation filtration. Then I have obtained the graphene quantum dots TiO2 nanohybrid as shown in the schematic. And the inside of this, the figure and the beaker solution is representing the photo of this graphene quantum TiO2 structure solution. And further, I have done the one of the application of this hybrid nanostructures of graphene quantum TiO2 is the high degradation of methylene blue. So this is one of the degradant which is generated from this industries. Most of the colors that is polluted water. So in order to make the purity of water, so we have to degrade the methylene blue into water. So this is the experimental procedure where we have done the photocatalytic activity. So first we use some methylene blue in the liquid and dye catalyst and stirred for 1 hour. Then after that the concentration of this dye and catalyst solution is illuminated with a visible light, and every 50 minutes we have taken some amount 5 ml of sample and we measure the visible absorption spectroscopy that we will discuss later. Okay. These are the fundamental characterization technique to characterize every material, that is XRD. So these are the list of the sample codes. One is T0 means milling, and T0 TiO2 is 0 milling time, and the GQD is the hybrid of T0 GQD means T0 sample with GQD. So next we have done ball milling for different times of intervals like 4 hour, 8 hour, 12, 16, 20 like that. But we have chosen only the particular sample that is actually showing the best results. So that is T0 and T16 for comparison. So that results we can also available that Journal of Alloys and Compounds. Okay. And you can see the XRD pattern of this crystalline bare materials and hybrid nanostructures, where the GQD is showing the characteristic of 002 plane, which is the related to the interlayer of this layer structure. You know that the graphene is, the crystalline graphene is single layer, but if it is fabricated from the graphite flake, that is a layer structure, right? So the interlayer distance between the layers of this GQD is 3.34 nanometer. And also you can see that T0, different samples of T0, GQDS and T16, they are showing the characteristics peak of anodized TiO2 as well as the graphene quantum dots. And we have also obtained there is some new peak that is related to the in the TiO2 sample, the Ti3O5, which is the new phase of TiO2, which is formed due to the ball milling techniques that we have reported in this Journal of Alloys and Compounds publication. So next we have this first figure is showing the TiO2 nanoparticle without ball milling. That T0 is showing the around particle size is around 80 nanometer. Corresponding IFT image that is P is showing the 3.25 angstrom, which is the plate 1. That's okay. Next, the figure C is showing the graphene quantum dots, which average size of 5 nanometer with the layer the distance of 3.34 is corresponding to the interlayer.
Dr. Gunirajendra. So you're not audible. Please unmute. Okay, Dr.
Yes.
Your work is related to,
yeah.
Annotates of TiO2, right? You have shown
yes,
that morphology
yes.
set ISNA is at SEM micrograph, is it right?
Yes,
okay.
TEM images.
Could you tell me what resolution you have taken the SEM micrograph? I'm talking about the instrument resolution.
So this is so that the figure B, I think based on the figure B, this is IFFT image. That is not actually the result obtained by the TEM. This is IFFT. That means HRTM image only, but we filtered by Fourier transform, then we obtained that.
So you might not know about that the resolution of that instrument.
Yes. It's not not exactly that one angstrom. Okay, next the figure D is showing the T16 ball mill sample, and the figure E is showing the T0 GQD sample with the TM image, and the figure F is showing the high resolution TM image of GQD and TiO2 sample, which come from this formation of GQDS and TiO2 hybrid structure. And G is also showing the T16 GQDs with there are some black spots, which is the TiO2 is coated on the graphene quantum dots, and there's corresponding high resolution TM image shown in H. And I is the after photocatalyst we have taken the TM image that is also showing the conformation of GQD TiO2. And further we calculated the Raman studies which is showing the characteristics peak of antennas TiO2 as well as the graphene quantum dots, and which is you can see the different figures are showing the characteristics, and figure B showing the shifting in the blue shift in the blue shifting of Raman even peak of T antennas TiO2 strong, indicating the very strong interaction between the graphene quantum dots and TiO2. So their shift is in T0 GQD is 5 centimeter difference compared to the T0, and T16 GQD showing the centimeter inverse difference between the T16 Ag1 peak of the TiO2. So this indicating very strong interaction, and the insert in the figure here showing there is a inner to n of results we have in the large that is where actually we introduce some new peak in between that Ag1 B1G peak and CO-TI bond is a new peak. So that we confirm.
Okay, okay, Dr. Goni Rajendra. Okay, okay. So now we are presenting your already published work, is it right?
Yes, yes, sir.
Yeah, okay, okay, fine, fine. Okay, fine.
So can I go on?
Mr. Arun Kumar, now you please stop sharing. We'll go for the next the presenter. Mr. Arun Kumar, we have given the
so let me discuss the application part. Sure, application point.
We have already, we have already seen that PPT. Okay, no problem. Can
okay,
stop sharing.
Okay.
We'll go to the next presenter. Mr. Arun Kumar, we have given the.
Yes, sir.
Yes, fine. Now you can start with share your screen. Mr. Arun Kumar, your talk time is
yes,
5 minutes. 5 minutes.
Yeah. Fine. Okay. Good morning, everybody. Myself, Arun Kumar from Bangalore University. I'm a PhD scholar. Fine. Let's talk about today's topic. As like the previous talkers, I don't have a much colorful pictures. Rather, I hope you people will, my data points will attract you much more. I hope. Fine. So, as you are all aware, alpha, beta, gamma rays are potential illness-causing nuclear radiations. And among these radiations, alpha and beta can be easily stopped just by paper or some metal sheets. But the gamma rays are highly penetrating radiations and highly ionizing radiations. So it can cause severe damage to living system. So what happens during interaction with the matter? I mean, the gamma rays interaction with the matter, it loses its momentum by transferring to the electrons so that the material gets ionized. So we need a large electronic clouds in order to attenuate them. And in order to provide the large electronic cloud, we need a high-Z material. Okay. But the problem with the high-Z material is most of the high-Z material is toxic. For example, the conventional material is lead. So we need to provide an alternative material to the lead. So in that direction, studies have shown that polymer and are much radiation resistive, particularly hydrocarbon chains are much more stable with our radiation than carbon with other elements. Okay, and therefore the polymer resins can tolerate gamma radiations to varying degrees, allowing them to be suitable for various applications. So since these radiation resistance doesn't give the opaqueness, okay, so we need a radio opaque powders to introduce. I mean, radiation resistance shows that how with stability is the material with respect to the radiation, but it cannot stop the radiation. So the radio opaque powder become more popular. However, these polymer resins are plastic which are non-biodegradable. Now the point is, why should I look at it? Because in order to develop a material to be sustained and eco-friendly is much more required.
Mr. Arun Kumar, you can skip the introduction. You can directly go to our work. please.
Yeah.
Yeah, you can skip the introduction. Please write.
Yes, sir. So we are looking at the material which is eco-friendly and that are hydrogels. Fine, here in the case, I'm directly moving to the topic. So I have chosen a hydrogel, which is going to be the eco-friendly material. And along with this, I need to choose a hydrogel material, which should be uneco-friendly. So that I have chosen here the bismuth and tungsten. Both are being an eco-friendly material, and also this PVA hydrogel, particularly which I have chosen, also an eco-friendly material. In combination, we are supposed to get a very good eco-friendly material. Let's see how this material is going to perform with respect to the attenuation property. So here I have taken the first parameter, the mass attenuation coefficient. So when here everything I have calculated through the XCOM and XMO database system. None of these samples were tested experimentally. So why it is? Because we need to check the material's capability before entering to the experiment. So we are doing this through this XCOM and XMO database system. Fine. The mass attenuation plots here we can observe. I hope my cursor is visible to all. At the lowest energy range, we can observe here the image absorption with respect to the tungsten PVA composite and bismuth PVA composite. When compared to these peaks, the tungsten PVA composite peaks are much higher when compared to the lead, the conventional material. So which means it can give you the much more radiation resistive, opaqueness when compared to the lead, the conventional material. However, it is in low energy range. Let's see the furthermore. Here I have taken the linear attenuation coefficient, which is similar to the mass attenuation coefficient. Here also we can observe and confirm that the tungsten PVA composite has a very good radiation resistance when compared to the lead and bismuth PVA composites. And here the next one, the atomic cross section, and it is also confirming that when compared to the bismuth PVA composite, the PVA tungsten composite are providing a much more radiation resistance and radiation opaqueness properties. So it is showing that it is very good material at the lower energy. But when it comes to the real life experience, we need a material for the higher range also. Let's go further. Here I'm observing the electronic cross section of the material, and it is also giving the similar pattern, and there is no much difference. And here I have taken the effective Z of the material. Here you can observe clearly the tungsten PVA composite has lower Z effective when compared to the bismuth PVA composite. It's quite natural because bismuth has a high Z when compared to the tungsten. And here I have made, you can observe clearly, I have varied the filler rate to 10% to the 70%. Done. So I'm getting the very good interaction rates, everything to the 70%. And the next one is the most important one, is the half valley layer. Here we need to look at something a bit more seriously and carefully, because we need a radiation shielding material to be thinner. Why? Then only we can use this material for the real life applications. Here, one more thing we need to be noticed, that these PVA hydrogel films are flexible and stretchable. So if we can able to a thinner material, with the lowest half allele layer material, it can become a potential promising material to the future. And here I have mentioned the half allele layer for the conventional cobalt-60 energy range, that is 1.173
MeV and 1.33 MeV. Here you can observe that the black line indicates the half a layer line of the PV, I mean the conventional material. And whereas the green line is depicting the 70% weight% of the PVA tungsten composite. Fine, which is much lower than the lead. And along with this point, I would like to point out you one more thing. You can observe this, even the 40 weight% filler rate PVA tungsten composite, it is giving almost equivalent to the lead. I mean, you don't need to go for even 70%. Even with the 40%, you can get the more or less equivalent half a layer equivalent to the lead. I mean, the PVA tungsten composite. And it furthermore, here I have tried to measure the 10th value layer of the material. I mean, the half a layer, which means a layer which can reduce the intensity of gamma rays to the 50%. Meantime, the 10th value layer defines the 10% of the reduction in intensity. Done. So it is clearly showing that this tungsten and PVA tungsten composite with 40%, 70% filler rate, giving a very good attenuation when compared to the PVA bismuth and with lead. Done. So here are the certain data which are already published. Here I have taken the 0.662 MeV or 662 keV gamma photons
okay,
radiation.
Mr. Arun
Yes,
Kumar.
sir.
Okay,
Yeah.
fine. Please, okay, stop sharing your screen. So, you did it that what the polymer material, especially
Yes,
that the hydrogen composites and the radiation
exactly.
properties were given. Okay, fine. So, do you, what are the problems you identified in this work?
Sir, primarily here I have made everything the computational technique part. I mean, I have calculated everything theoretically. Okay, so it is need to be work it out with the experimental part too. But here we have a very good. The problem is I didn't find anything like that, because we have very good theoretical support which has been done from the last few decades. So I don't think any problem.
Okay, fine. Okay, fine. So please stop sharing the screen. Fine. Thank you. Thank you for your presentation.
Thank you, sir.
Yuvarani ma'am. Yuvarani ma'am. Am I audible, ma'am?
Dr. M. Yuvarani.
She is there.
Ma'am, Yuvarani ma'am, can you please join in the Microsoft Teams link, because the speaker has arrived. Yes, Sanju ma'am, you can start.
Yes. Good morning, everyone. Once again, I welcome you all again to day 2, session 3 of our conference. Our next speaker is Rohit Mehidwal from Singapore, and I request Dr. K. Subramaniam, Assistant Professor, SRMIST, to introduce our speaker to audience. Sir.
Welcome, Dr. Rohit, sir. Rohit, sir?
Yeah.
Welcome. Hi.
Yeah, hello.
Hello, hi. Good morning, everyone present here. I'm very happy to introduce Dr. Rohit Medwal, Research Fellow, Natural Science and Science Education, National Institute of Education, Nanyang Technological University, Singapore. Dr. Rohit has completed his PhD in Department of Physics and Astrophysics, University of Delhi in the year of 2013. And remarkably, he is the Anil K. Bharti Bharat Nagar Awardee for Best Doctoral Thesis in Solid State Physics from Indian Physics Association. He has completed his postgraduate in University of Delhi. He has completed his undergraduate in University of Delhi. His research area.
Subramanian sir, your background, what is your background?
Sorry. His research area includes nanomagnetism, spin transport technologies, quantum spin photonics, inside and operator electron nanoscopy. His H&X is 11 and he has published more than 80 papers in international journals. He has bagged many awards. He is an auditor of the Indian Institute of Physics, Singapore, in the year of the 2020. He has one gold medal awardee and one bronze award in the Singapore Science and Engineering Fair in the year of 2020. He secured 3 gold awards from Nanyang Research Program, Singapore, in the year of 2019. He got 2 gold awards from the Nanyang Research Program in 2018. He is the mentor the Sakura Science Program, Japan, in the year of 2017. He is doing the research funding amount of 35 lakhs US dollar. He has his ongoing project, the number of projects is 8 projects. We have very proud to you have to be in part of the international conference, sir. So now you take the session.
Thank you very much. With this, maybe I would like to share my screen. So I'll just go with the screen sharing. So yeah.
Beena ma'am, please mute your mic, ma'am. Dr. Beena ma'am, hello. Hello, ma'am, Beena ma'am.
Yeah,
yes, sir. Rohit sir, please. Sir.
Yeah. I muted her mic. Sorry for that.
Yes, sir. Now you can proceed, sir.
Okay. So thank you. The work is which I'm going to demonstrate or like the present here is mainly done in NI and then QTech, QC Institute of Technology, Japan, where I'm associated. I'm visiting researcher there. And with this, I would like to start my talk. Today, I'm going to talk about the controlling and probing of the spin current. And people are generally talking about the electronic current, and they are trying to develop new devices like using the electronic currents. We are like the electrons, we are making the transistors, we are making the switches, and we are making all the different type of current today's CMOS technology devices like the computer, all based on the CMOS technology. But we are ahead of this. We are trying to reduce the power consumption of these devices. We are trying to use the new fundamental principles where we can use the spin of electrons to make these devices and to realize these devices at ultra low power scales. So that is my main focus of the research here, and we are working mainly on these directions. So with this, the research directions which we are heading ahead in the spin transfer technology, we are trying to develop new systems, new techniques, and new materials for spin Hall effect, like the normal Hall effect, where we can separate the charge by applying the magnetic field. Similarly, we have the different materials which we call the spin Hall materials, where we can apply a normal charge current and we can spin polarize this charge current into the 2 different directions. That is called the spin Hall effect. And we can convert this spin current back into the charge current, and that is inverse spin Hall effect. We can also working on the spin pumping, where we can allow the magnetizations to persist and generate the spin current, and we can pump this spin into the from one layer to another ferromagnetic layer, or one ferromagnetic layer to another materials which are not ferromagnetic layers, and transfer this information from the one place to another place using the spin waves, because we can only propagate this informations without passing the charge currents. Generally, today's technology, we are using the charge current. We are allowing the charge current to pass from the one state to another state, and which is carrying the information from the one place to another place. Whereas in the case of the spintronics, we are not even let the charge to pass through the material. We can even transfer the energy, or you can say the angular momentum, from the one place to another place without moving the electronic charge physically. So this is the spin wave. We work on the spin wave, and then we utilize them for the domain wall motions, which is like the Professor S.S. Parkin is really working on that directions, where we can develop a new restrict memories. And with this, I also like to tell you that we are working on the spin photonics, where we are exciting the ferromagnetic materials using the ultra short pulses lasers, and we can generate the terahertz photons. And we are working on the ultra fast magnetism, which is a femtomagnetism, for which we are talking about the time scale of femtoseconds, how these spins are being pumped from the ferromagnetic material to a heavy metal. This is just a glimpse I'm giving. Later I will go into the slowly basics, and then how we are developing these systems I will explain. And for this type of systems, we are working on the ultra fast spin transport and ultra sensitive sensors we are trying to develop using these techniques. And the third expertise which we are working, this is quite new and quite interesting. People are using the TEM for just seeing the imaging, and just try to see the domain structures, or like you can say the normal imaging, like particle size, or you can say the crystallographic orientation using electron diffractions. But here we are not interested in that, the normal imaging schemes. We are interested how we can use the TEM for designing the experiments, which people don't do. What we are doing, we are trying to pass a current, we are trying to apply the voltages during the TEM measurement, and we are seeing that how those domains being formed, how these domains can be changed from the one state to the another state, and how these domains can be, whether they are magnetic or non-magnetic. We can do the long-range microscopy, we can do differential phase contrast imaging, and we're trying to see that we can investigate these magnetic domains in the TEM. And at the same time, we are trying to develop a new chips. I can show you this. You can see that here on the scale. We are trying to develop new holders for the TEM, new chip for the TEM, where we can just do the spin transport measurements during this TEM imaging, so that we can see that how in situ imaging during the in situ process. I'll show you an example that how we can use a spin transport to really move the domain wall from the one state to a state, another state, so that we can store the informations. And with this, and I would like to thank the Subramaniam that he has explained that I was working on nanomagnetism. For this, I have been awarded the Anil K. Bharti Bhatnagar Award. I was mainly working on nanomagnetism during my PhD, which is really a suitable candidate for the heat-assisted and heat-dot recording media. And recently, the Seagate company has just launched a heat-assisted recording media using the same system, FEPT system, which I was working on during my PhD. So with this, I would like to go in the detail what we need to why we need the technology. Today morning when I wake up and I start thinking about the SRM talk, and then okay, I just searched the SRM University. What I found that enormous amount of results in 0.63 seconds. It's just 1.7 billion results. Such enormous amount of data in ultra short time scale. How it is possible? This is only possible if we are developing these technologies also slowly. By improving the storage information technology, process information technology, and transferring information technology. And this is possible because of the mainly two devices, which are memory devices and logic devices. So we are trying to develop these memory devices and logic devices. Memory devices are used to store the information, and the logic devices is used to transfer and process the information from the one place to another place. So, and their integration, that is a key integration. That is a key factor which we have to think that how we can integrate these devices, because they have to talk to each other for transfer the stored information in the system to process from the one state to another state. So this integration is very, very key challenging part. And people are trying to talk about this integrations by the several schemes like the neuromorphic computing, and they are trying to develop a new architectures where they are saying that we will try to develop a brain-like structures from the system. And from this, we can make the digital world, where we are giving the platform. We are using this platform to deliver a talk. And imagine that if we have been storing these informations day-to-day life, and by 2025, we can have 35 zettabyte data, such an enormous amount of data, and how we can store this data and how we can process this data is a challenging task for the entire universe. Imagine we have been storing this information in the DVDs, and what we could have got, we could have stored the DVDs in the huge amount of DVD that you stack these DVDs one over the other. You can have a drive over the moon using the DVD. Thanks to technology, which we have come from the 20th century, we were using the Ampere's law, where we were applying the charge current through a conductor and convert this conductor to a magnet, like because of the Ampere law. And to our 21st century, we are using the spin transfer torque, where what we do, we pass the charge current to a ferromagnetic materials, make the charge current spin polarized charge current, and convert the inductor into the spin current. So this technology, the 20th century technology, which we are using the Ampere's law, is also important, and where the system was bulky and it was power hungry. Whereas the systems which we are using here, the spin transfer technology, is very miniaturized system. The system dimensions are very low and it's not power hungry. And it's utilizing the spin polarization, not only the charge current. So thanks to this technology, we have developed the spin polarization technology using the spin transfer torque technique, and we can use this for the spintronics, which is the recent era of the research. Where, and let me define this, what is this different type of current for the students? If the charge current, in the charge current, with this which we call the unpolarized current, we have the population density of the upspin and downspin is same. So as a result of this, what you observe that you have a net flow of the charge current. Moment you pass this charge current through a ferromagnetic materials, which has the magnetization direction in around the one directions, what will happen? You will see that based on the direction of magnetizations, you will observe the spin polarizations which is passed through the ferromagnetic materials. And as a result of this, you will observe the spin polarized current. And this spin polarized current simply define that you have a population density of the upspin is higher as compared to the population density of the downspin. And as a result of this, you can see that this will nullify and give rise to the charge current. And whereas this extra spin current, which is spin polarization, will give rise to the spin flow of angular momentum, which we call the spin current. What about the pure spin current? When this charge current is passed through the unique materials, which is called spin Hall materials, and where we have the spin orbit coupling is very high, or you can say that because of the relativist effect of the spin orbit coupling in the material, what we will observe clearly, there is a two different channels of the spins, which is the spin up spin is going in the one direction and down spin going in the another direction. And this is what we call the pure spin current. There we don't have any charge current flow. We only have the propagation of the angular momentum, which is we call the pure spin current. Or we can say simply the flow of angular momentum in the quantum mechanical term. And how we can generate this charge current on the spin current is quite challenging. And people are trying to find this several schemes through which they can convert this charge current into the spin current. We are also working in the several schemes. I'm mainly focusing on the two aspects. It's difficult to do all the aspects together. So we are mainly working on the first, where we can use the electricity to convert the charge current to a spin current, which we call the spin Hall effect, where what we do, we apply the charge current through a conductor, which has a high spin orbit coupling, or we call the spin Hall materials. And because of this spin orbit coupling in the material, what will happen? They will the charge current, unpolarized charge current, which is passing through, they will get the spin polarized. And as a result of this, you will start accumulating the spin polarized current at the interfaces. This is called the spin Hall effect. And we can convert this spin, which is being generated, back into the charge current using the inverse spin Hall effect. And this is called, this is the vice versa of the spin Hall effect, which we are talking about. So I will show that how we can use this spin Hall effect, inverse spin Hall effect, here in the device geometries which we are working on. So there are two different schemes which we are working on, spin pumping and inverse spin Hall effect, where we are trying to magnetization to precise about the applied magnetic field, and which give rise to the polarized spin current. And we can convert this spin current back into the charge current using the inverse spin Hall effect. That is the first technique. Second is we have also used a spin torque ferromantic resonance, where we can convert this charge current into the spin current. Please make a note on these two techniques. The technique number one is the spin pumping inverse spin Hall effect measurement technique is for spin to charge conversion, whereas the technique two, the spin torque ferromantic resonance, is for charge to spin conversion. So these are the two techniques which we are working on. I will show for the generation and detection of the spin current using the electrical detection means. So what we are doing in just an example, I will give you the schematic how we are working. So we have a ferromantic materials FM, which is interfaced with the platinum, which is a spin Hall material. Platinum is a spin Hall material because platinum is having the high spin orbit coupling. And the ferromagnetic material has spontaneous magnetizations. As we all know that the ferromagnetic material has spontaneous magnetizations. The moment you apply the external magnetic field, this magnetization will try to go aligned to the direction of the applied magnetic field and will try to oscillate and then try to go to the direction of the applied magnetic field. But to allow these magnetizations to persist, what we do, we apply the external magnetic field, HRF, in the orthogonal to this, and which will allow the magnetization, they will pump the magnetization to its own states and will allow these magnetizations to have the sustained precision about the external magnetic field. And this is how we excite these magnetizations to persist about the external magnetic field. And this where the what is this theta c is a precision cone angle, at which cone angle this at what angle this is persisting. This is a precision cone angle, which is also an important factor when we are trying to discover the spin Hall materials. So this is the precision cone angle, and magnetization is persisting about the effective magnetic field. And this persisting magnet will allow the spins to pump into the platinum. And this is a source of a spin current. This persisting magnet is a source of spin current, which will inject the spins into the platinum. And we can use the inverse spin Hall effect, which I explained you, to convert this spin into the charge current. And this charge current will generate a voltage across the platinum, and we can measure the voltage across the platinum. And this is the voltage which generally measured. This is the microvolts in range. Interesting aspect is here, how do we know that this is a pure spin voltage or a spin motive force, the voltage generated because of the spin motive force? So we can clearly see that when you have the positive magnetic field, you can see the polarity of the spins of voltage is high up, the positive. When you reverse the direction of the magnetic field, the voltage signals reverse. So this clearly shows that we have the spin motive force which is responsible for this spin Hall voltage. So this we have clearly shown that we can generate the spin voltage by the persisting magnetization and can detect using the inverse spin Hall effect techniques. And this inverse spin Hall effect voltage mainly depend on the two contributions. One is the spin precision cone angle, that is the theta sh, we call the spin Hall angle. What is the conversion efficiency of this spin which has been pumped from the ferromagnetic material to a platinum, number one. Number two is the spin current. What is the conversion? What is this amount of the spin current which is being pumped from the ferromagnetic material to a platinum? So these two factors are very important and really contribute to the voltage which we are measuring, which is a VISHE, or we call the inverse spin Hall effect voltage. So this, I would like to highlight that this spin current which has been pumped from the ferromagnetic materials to a platinum mainly depend on the two factors, like the spin mixing reluctance, this is G mixing, and then theta c, which is the precision cone angle. Just now I explained you, because when we are trying to pump the spin current from the ferromagnetic material to a platinum, there are two contributions. What is the interface? Whether the interface with the platinum of the ferromagnetic material is very clean, that is defined by the spin mixing reluctance, and what is the precision cone angle of the ferromagnetic materials, which we are applying the HRF to allow the magnetizations to persist. So these two factors are very important, and we try to find out what are the main reasons for the accurate estimation of the precision cone angle, or you can say the estimate accuracy of the spin Hall effect in the platinum using this method. So we try to find out the precision cone angle by 4 different means using the AMR. using the power transmission. I will not go into the detail of these things, and using the power absorption and using the fixed input power. So I will give you the directly takeaway message from this. This is very important techniques, 4 different techniques which people are trying to investigate, and then we try to compare this all 4 techniques to calculate the precision cone angle. And what we observe clearly here, this all 4 techniques give the different precision cone angle. And when we try to calculate the spin current, estimate the spin current from this precision cone angle and mixing conductance, but we observe that 4 different method is giving the 4 different spin current. So it is quite confusing that people are thinking that the spin current for the power input is higher, power absorption is linearly increasing, for power transmission is decreasing, and for AMR is increasing and decreasing. So which is true, because the same device, different methods are giving this different results. So what we did, we also try to measure the inverse spin Hall voltage from another device, another set of device with a different device configuration. And what we clearly observed that initially for the inverse spin Hall effect, this is the final result, because this is the final output we have to correlate, and this is the intermediate results. So what we clearly observed that initial frequencies, it just increases, and after that it start decreasing, and which is clearly matching with our AMR signal, AMR results. In the AMR results also, the spin current first increases and then decreases. So this, when we try to measure the spin current from the AMR and the voltage from this VISHE, and we put this VISHE, the GS spin current and the VISHE, what we observe clearly the spin Hall angle, and which is a frequency invariant only from the AMR effect. This is also the frequency invariant from the power absorption, but the absolute value is not correct. The absolute value plus the result, plus the behavior of the spin Hall angle in the platinum is only true when we are measuring the signal from the AMR, signal from the AMR method. So this was a very quite good discovery, where we were able to show that for the longer range of the frequency, we can have the frequency invariant spin Hall angle in the platinum. So generally people were trying to report the spin Hall angle for the lower range of the frequencies, and then say this is the percentage of the spin Hall angle. But you can see that if the people are reporting from the power transmission, here they can say the spin to charge conversion in the platinum is 30%, where they can say this is 10%. But ideally, theoretically, is 5 to 7%. And we have successfully demonstrated the frequency invariant spin Hall angle in the platinum using the AMR is around the same what has been predicted theoretically. This was the first discovery. And then what happened? How we can improve this pumped spin current into the platinum. Can we control this pumped spin current into the platinum? That was another challenge which we were trying to consider. So for that, we are trying to see how we can do that. So for this, we designed a special material, which is yttrium iron garnet. We called it YIG in the beginning. And what I did, I tried to control the anisotropy of this YIG by growing them on the different directions epitaxially. So we grow these YIGs on 001, 011, and 111 on the same orientation of the substrates. And we took quite long time to grow them in a very perfect manner, so that they really follow the cubic anisotropy and uniaxial anisotropy and non-cubic anisotropy in the 111. And we can clearly see here, there's a 4-fold symmetry which dominates the cubic anisotropy. In the 011, we have a dominated uniaxial anisotropy with a small amount of the cubic anisotropy, and there is no significant cubic anisotropy in the system. So we were successfully able to demonstrate this in our APL paper, and then ACS applied material interfaces paper, where we clearly show that we can control these anisotropies and we can control this various parameters in this system. And finally, we made the devices out of it. And we chose the 2 material system. One is YIG00, 001, where we have the perfect cubic anisotropy in the system, and the YIG111, where we don't have the cubic anisotropy in the system. And we made the device, and we measure the inverse spin Hall effect signal. That is very common. Everybody can do that. That's not interesting, because we have been doing this from the almost 10 years that we can measure the spin ISHE voltage in the system. The interesting part is how we can modulate this spin current in the system. So this spin current which is being pumped into the platinum mainly depend on the 2 contributions. One is the mixing conductance, and second is the precision cone angle, which I was discussing that these two contributions are dominating. So for YIG 111, what we observe that the symmetric component of the voltage, which we are measuring, that I just show you the peak, which maybe I can show you, I can draw here the signal, which is, we have this signal, which you can say this for the positive and the negative, the ISH voltage. So the symmetric component, the voltage across this, the symmetric component, the amplitude of this, when we plot as a function of the phi, it should follow the sine theta, because the spin current and the direction of spin and then direction of polarization of spin, charge current and then spin, they are orthogonal. So they should follow the sine theta behavior. But when we do these measurements on the YIG 100, what we clearly observe that we can modulate this sine theta into the sine theta plus 4-fold symmetry in the ISH voltage. And that is clearly dominated by the HR resonance field plus the anisotropy field, or you can say the delta H line width in the ferromagnetic resonance spectra. This was quite resemble, like all are perfectly in order. And we were able to clearly distinguish these two effects, and we try to deconvolute, which I will show in the next slide. But I would like to highlight here, the YIG 111, there is no cubic anisotropy, we have a perfect sine theta behavior. Whereas YIG 001, we have the sine theta plus the 4-fold anisotropy, or you can say the modulation over the sine theta behavior in the symmetric component of the ISH voltage. So this, we try to deconvolute. We can say that this is because of the anisotropy, but what is affected? Is the spin mixing reluctance affected, or the precision cone angle is affected? So we try to deconvolute what is the main cause of this precision cone angle, or main cause of this modulation in the anisotropy field, or you can say the spin current. So we try to calculate the spin mixing reluctance, and we theoretically and experimentally calculate this is within the error bar is almost constant. There is no much change in the spin mixing reluctance. I will not go into the detail how we are going to estimate the spin mixing reluctance. That's a very long process. But I would like to highlight that this is almost constant. But whereas when I measure the HRF for precision cone angle, what I found clearly, I will see the 4-fold anisotropy along with a uniaxial anisotropy in the system. And that is because of the power absorption measurement. This is a separate measurement done from the device measurements. Device measurement is a separate measurement, and these measurements are really separate measurement. And both the measurements shows the same effect, exactly same effect. And when we deconvolute this, we clearly observe that we have a sine theta curve because of the ISHE symmetries or the device symmetries which we are getting. And we are also adding the one more contribution of this ISHE voltage, which is the anisotropic contribution coming from the crystal field anisotropy field from the system. And this is the first demonstration we are able to so clearly demonstrate that the anisotropy of the ferromagnetic materials also purely affect on the inverse spin Hall effect voltage. So this is the publication we are going to submit soon. And we can also convert this charge. Now we are talking about the spin to charge, but we can also convert the charge current to a spin current. And we are trying to design the new materials where we can improve the efficiency to convert this charge current to a spin current, because ultimately we have to have the devices which has a higher conversion efficiency so that we can make the device function at really at low power consumption. So for what we do, we apply the IRF current into the platinum, which can generate the Oyster field into the system, which is shown here. As a result of this ISHE, the spin Hall effect, we can generate the spin current into the ferromagnetic materials, and which this spin current will exert a torque on the magnetization, will allow the magnetizations to precess. So this magnetization will start precessing, which is completely a reverse effect, which I explained you in the spin pumping inverse spin Hall effect. This is the spin torque ferromagnetic effect, where we are using the torque from the non-magnetic materials on the magnetization vector of the ferromagnetic material to allow the magnetizations to precess and detect the signal. So for this, what we are doing, we are trying to design the new materials where we have several materials which we are trying to design. And so as I've shown you that the conversion efficiency for the platinum is only 5 to 7%. Can we improve this conversion efficiency in the platinum? So for this, we designed this new material. We try to implant the material heavy metal, platinum and tantalum. And we can see that because the spin orbit coupling Hamiltonian is tightly proportional to the potential gradient, and which is the breaking of the symmetry at the heterointerfaces, and we can clearly increase the spin orbit effect in the system which has a broken symmetry. So utilizing these basic fundamental concepts, we design a material. What we did initially with the TEM, we have this processional TEM. So we have a platinum, we did to the 10 nanometer platinum. We implant the 10 nanometer platinum with a sulfur, keeping the same thickness. So after implantation, our thickness is not modified, it's almost same. We did the electron energy loss spectroscopy to see that the percentage of platinum is implanted, percentage of sulfur is being implanted in the platinum. And you can see that the uniform distribution of the platinum in the uniform distribution of the sulfur in the platinum, and we have a clear implantation of platinum, clear implantation of sulfur in the platinum, and we call this is PTS, and this is around 10% with the depth profile. And we also confirm from the XPS there is a bond formation from the PT and S. You can see that there's a after deconvolution there is a shift in the two peaks, which clearly shows that the bond formation in the PT and then sulfur. And this is we call the platinum sulfide. After this, we made the devices out of it using the photolithography technique. And what we observe, we clearly see that the spectra which we record from the spin torque ferromagnetic resonance is for the platinum and the PTS. Clearly, there is an increase in the shift in the, there is clearly shift in the symmetric and antisymmetric component. So we can see that from this, I can maybe draw a line for the easy understanding. This is the shift I'm talking about. You can see that the shift is, the relative shift is higher in the case of the PTS as compared to the pure PT. So we deconvolute. This is symmetric component correspond to this correspond to the spin to charge conversion, and asymmetric component because of the Oersted field. And we can see that the symmetric component in the PTS is quite higher in compared to the pure PT. This clearly indicates that we have a higher spin to charge conversion. And this is the spin orbit torque symmetry, which is sine theta cos 2 theta, and which is also not broken after the implantation, because we're trying to do the low energy implantation to intact the symmetries of the platinum crystal. And when we do the real analysis after putting this S by A symmetric component to the asymmetric component ratio, and then putting all the constant parameter in the system, we're able to observe the 3 times enhancement, or you can say the 30% spin to charge conversion in the PTS. And we were able to place this material among all the PT derivative till now discovered is one of the best candidate, and even have the highest spin to charge conversion, 50% at 10 Kelvin. And this article is really appreciated and has been published in the Advanced Quantum Technology as a featured article in the front cover page, where we are able to produce a new material saying that we have low materials which can really give the low power meditation switching in the MRAM applications and can be used for the microwave generations using the spin torque ferromagnetic resonance. Now the question is how we can improve the frequency which we are working on the 10 gigahertz range to a higher frequency, because we are trying to develop a system where we are talking about the ultra dense universe to our ultra fast universe, because we need to transfer the information from the one state to another state at ultra fast time scales. So for that, we are also working on the different schemes. So what is the question, like how we can go for the microwave region to a terahertz region? So we come with a new idea where we can shine a light on the ferromagnetic materials. We can excite them really far out of equilibrium, and we can use the relaxation processes which are in the femtosecond time scale, or you can see the picosecond time scales, to get the ultra high frequencies processes to make the devices. So what I'm talking about, maybe I will just explain in detail in this slide. So first I will explain the very fundamental phenomena, which is the ultra fast demagnetization, and which has been discovered in 1996. What people are trying to say here is, when you shine a ferromagnetic materials on the ferromagnetic material, what you will observe, there is a quenching of demagnetization, with quenching magnetization, or you can say that's demagnetization. This quenching is basically very simple to understand. It's very phenomenological model like the Curie law. Where you have ferromagnetic materials, the temperature is low. If you keep increasing the temperatures, you can really destroy the magnetic order in the ferromagnetic material. So this is what we observe most of the time. If you heat the magnet, you can make the magnetic non-magnetic material. But the question is, one can understand easily. The question is how fast this quenching is happening. That is very interesting. If you see the time scale here is 100 to 300 femtosecond time scales based on the material. That ultra fast time scale, the quenching is happening. And this really drawn a huge attention of the scientific community, where people are mainly working on the photonics community. And people are trying to integrate the spin, because they are magneto-optic community and then the spintronics community, and then all merged together, they made this for the spin photonics community. And they really got the attention of these results. People are trying to explain this by the several means. They were saying that this is because of the electron scattering. When you shine a light on the ferromagnetic materials, they were also talking about the electron phonon scattering and electromagnetic scattering. But one should not forget the time scales of these scattering events. They are different. So if you talk about the electron scattering at the ultra fast time scales, this law is within the less than 100 femtoseconds. Electron phonon scattering, because your phonon lattice should not disturb, it generally happens in picosecond. But magnons are like really beyond the picosecond, it comes in the nanosecond time scale. People are also talking about the super diffusive spin transport, where they're saying that when you shine a light on the ferromagnetic materials, you can really allow the spins to go away from the one area to the another area. Because when you shine a light, these electrons are really hot electrons. They are really far above the excitation energy. They are above the Fermi level. They are really randomly scattering. As a result of this scattering, they are trying to move from the one area to another area. So this basically effect is very dominant in the spin transport community. So I will explain in detail what I'm talking about in the super diffusive spin transport. When you shine a light on the ferromagnetic material, what happens? Basically, you excite the ferromagnetic materials, and there is a minority and majority spins in the system. As a result of this excitation, the minority spins are scattering, and as well as the majority spin also scattering. This minority spins scattered more because they're less in number, and their lifetime is lesser. The scattering and the group velocity is quite low. So as a result of that, they never diffuse into the heavy metal adjacent to it. Whereas this majority spins, they are in main number. They are the scattering events less because they are in the phase, and they try to go and then pump into the adjacent heavy metal. And as a result of this, there's a quenching of the magnetization of ferromagnetic. There is induced magnetization of the heavy metal because the spin has been pumped into the heavy metal, and which set up a spin current into the heavy metal. And this transient spin current, which is 100 to 300 femtosecond, just now explained, because of the magnetizations, give rise to a terahertz photon. Because as we know that any radiated charge give rise to a radiation. So this terahertz photons, because they generally lies in the picosecond time scale, and we have this terahertz photon. And this terahertz photon mainly because of the transient charge current, which is generated by the JC. And this JC can be controlled by the spin to charge conversion. As I explained you, we have a spin Hall effect and inverse spin Hall effect, where we can convert this spin current into the charge current using the inverse ISHA, and convert the spin current charge current to a spin current using the SHA. So here we are pumping the spin from the ferromagnetic material to a heavy metal by the optical excitations. So we can use the spin Hall effect of the heavy metal to convert this charge current or spin current to a charge current. One point. Second point is, what is the magnetization direction of this ferromagnetic material? So that can also reverse the phase of this terahertz photon. So these are the two important parameters which we have to consider for the next talk. So keeping in that mind, we design a materials system. We design a material system, platinum permalloy interfacing with the permalloy interfacing with the platinum. Permalloy is NiFe. I always call the NiFe as a permalloy. So NiFe, or the permalloy interfacing with the tungsten, which has negative spin Hall angle, and permalloy interfacing with the positive and negative spin Hall angle. So what I can clearly show you here, that for positive spin Hall angle, the terahertz electric field is positive, and for the negative spin Hall angle, the terahertz electric field is negative. So we can clearly show that This the superdiffusive spin transport phenomena, where we are talking about the spins which is being pumped from the heavy metal, from the ferromagnetic to a heavy metal, really dominate over the emission of the terahertz photon, not only the demagnetization. So that is the takeaway message from this slide, where we are talking about that by changing the spin Hall angle of the heavy metal, which is tungsten and the platinum, we can really change the phase of the terahertz photon. That is the first thing. And we can add up these two signals by interfacing this platinum permalloy, platinum with the permalloy on the one side and tungsten permalloy on the other side, so that the direction of spin current is reversed and net effect is the, if you vectorially add this all spin current and charge current, you will see that both are in the same direction, as well as you can see that this effect is additive effect. So we can add this too. So this is clearly shows that you can add the M, because M is magnetization is vector, and you can also change the phase of the terahertz photon by changing the spin Hall effect of the tungsten and platinum. If I record this pulse, especially the terahertz field as a function of the M, which I can control by applied magnetic field, what I can do that I can really see that the hysteresis loop, which generally observed from the VSM or vibrating sample magnetometers. So MH loop generally we measure from the VSM, or you can say that Monk measurement is also very common to measure this VSM. So MH loop in the system, but we are able to do the same experiment by mapping this terahertz electric field as a function of the magnetic field. And using this discovery, we have clearly shows that we are able to design this spintronics magnetometer, and which is really broadband terahertz source, and also the spintronics terahertz modulator, where we can control the cohesive field, magnetization, and then spin current by the intensity of the laser, by the heating effect, or by several means. I'm going to talk about this, how we can design this new spintronics emitters in the next slide. What we can do is, when we shine a light on the ferromagnetic materials, we can record this hysteresis. This is the blue one, you can see that, which I explained you just now. If you map the electric field as a function of the magnetic field, we can map this hysteresis. How, when you shine the light with enough energy, what you can do, you can deposit the energy on the ferromagnetic materials. As a result of this, you can quench the hysteresis loop. And this quenching is observed here. This is experimental evidence which we can quench here. And this quenching is, we can clearly see this quenching, and we can further quench it with the higher fluences. And we can see that the coercivity decreases, as well as the terahertz pulse amplitude is increasing. And utilizing this effect, we sit on the one magnetic field. We allow this magnetization quenching, the hysteresis cohesive field quenching, and we can switch the phase of the terahertz photon from the one direction to another direction by just optical mean. This is what we have shown this our paper. This is published in the advanced functional material. So we have the low temperature, we have our terahertz phase in one direction, but by changing the optical fluences, we can go to the reverse phase by sitting on the on one constant magnetic field, and this is called the photothermal switching, or you can say that the switching because the thermal energy deposited because of the laser heating. And we also try to develop a new model to do the switching not only optically through a magnetoelectric coupling, where we're trying to design these emitters on the PMNPT substrate, which is a ferroelectric substrate, and trying to see how we can control the terahertz field using the pure electric field, which is really an application part, because we cannot come with a laser and then try to develop a bigger system where we can modulate this spintronics emitters using the pure optical lights. Whereas we would like to do this effect using the voltages or current, though it is more applicable towards to the real device system. So we designed the system. We were able to see that by applying the voltage, we were able to see we were able to change the strain. This is the strain curve. This is the XRD as a function of the voltages. We have the system where we can apply the voltages during the X-ray diffraction measurements, and we clearly see that the peak is clearly shifting, and then this is following the butterfly behavior of the strain, and this is analogous to this. We also did the FMR, the ferromantic resonance, and we can see that the same effect is being observed. Though because FMR is done at the high field, so because of saturation, we really don't get exactly the same separation, but we see the clear signature of this butterfly behavior as clearly observed in the strain behavior. Now what we did, we apply the voltage and we see the MH loop. And we can clearly see that we can tune the hysteresis. You can see the shape of the hysteresis tuning as a function of the applied magnetic field. And we utilize this, we sit on this field and we measure the terahertz photon. The moment I change the voltage, I can go from the positive to this negative field, and I can reverse the phase of the terahertz photon just by applying the voltage. So this is the first scheme where we have purely shown that voltage can be used to modulate the phase of the terahertz photon, and purely voltage can be used for the moving the terahertz photons in the spintronics emitters, which are the terahertz photons. And we are also trying to understand these effects in the TM microscopy, which I just mentioned that we are doing this especially the TM with the Lorentz microscope and differential phase contrast imaging. So I would like to give a very basic example or like the explanation. What is this Lorentz microscopy? Basically, in the TM, we use the objective lens to focus the beam. This is the electron beam. We focus on the specimen using the electromagnetic field. So we use a normal solenoid coil to focus this beam on the sample. And if we are working on the magnetic sample, it's difficult to do the measurements because the field which we are using the TM is 2 Tesla. It will saturate most of the ferromagnetic materials. So it's impossible to do this type of measurements in the TM. So we have a special TM, which we call the Lorentz TM. We turn off this objective lens. We just really turn off this objective lens. We have another objective lens. This is the lower, this we call the Lorentz lens. We turn off this, so the specimen is under the field-free conditions. There is no external magnetic field of the sample. And this beams pass through the sample and carry the information of the basically the magnetic informations, and we focus this beam and then do the imaging. We also use a second technique, which is the differential phase contrast imaging. This is done in the STM mode, where we focus the beam on the sample and we can do the raster scan on the sample. And based on the direction of magnetizations, you can see that Lorentz force is very simple to understand, that based on the direction of the magnetizations, you can have the different deflections in the system. And this is my live examples, like we have shown here in the palm alloy, which we are working on, that this is a bright field disk. Before, like I can show that this is the bright field disk which should be without the ferromagnetic material, but this is the shift in the bright field disk after it's passed through the magnetic domain here. When we have the domain in the different direction, so we have the shift, exactly the opposite shift in the bright field disk of the electron beam, which is being focused on the fluorescence screen. So this is how we use, and then based on the shift of this bright field disk, we can really estimate the magnetic moment in the ferromagnetic materials, and we can see that what is the direction of magnetization. So these are the 2 techniques we are mainly working on, and this is the manuscript which we have successfully published in Accountant Chemical Review, and where we have clearly shown that when we pass a spin current into the platinum and utilizing this effect, we can convert this spin current into the charge current into the spin current, and this spin current will exert a torque on the yttrium iron garnet, which is a ferromagnetic material, and will allow this magnetization domain. This domain is moving from here to here to switch or you can say that to propagate the domain ball from the one state to another state, or you can say the magnetic domain. For this, we designed this. This is a TM holder. We designed this device. This is a YIG interfacing with the platinum, Al2-3, and then platinum cap. We cut it so that we cannot pass the current through the platinum. We can only pass the current through the thin layer of platinum, which is a highly pure platinum. This device, this entire device is the device structure, and this is our chip, the MEMS-based TM chip, which we integrate with this holder, and this is our real device, which we use using the focus height wave. We integrate this device on the chip. You can see this is this very white dot. This is the real device, which is 1 micron, and we put in the TM, and we clearly observe this results, which is quite interesting. You can see here that this is the atrium guided film, which is the image, just normal image. And when under the focus defocus image, we can see this is the magnetic domain. And how to confirm this is domain? Because we can switch the direction of this domain by changing the magnetic field. You can see that this white become white, this line become a dark line here. You can see that, keeping the same parameter constant. And this shows that we can able to switch the domain directions by changing the magnetic field. And we can also, you can see that this domain is here. Maybe I'll just use the marker to highlight that this is my domain wall. And we can use applied magnetic field to propagate this domain wall from one state to another state, which is come to here by this. So we confirm that this we can propagate this domain wall from the one state to the another state, and we did this in situ experiment with basically clearly current. So we apply the current to convert the spin current. You can see here, maybe I can show clearly here in this one where we can go with the spin current. Maybe here, this is the domain wall. This is the domain wall. My domain wall is here. You can see that. And moment we increase the current, we can see that domain wall is moved to with the 3 milliampere to the one state here. You can see here. Maybe I'll stop here. You can see that the 3 milliampere, we can move the one domain wall here. And at 5 milliampere, it can really go to the final state where go to the third state. So we are able to successfully move the domain wall using the pure spin current, and we were able to live in situ detect this in the microscope. So with this, we are also able to see the switching of the magnetization from the one state to the other state using the differential phase contrast imaging, which I showed that we have this is a bifield disk without applying a magnetic field. But when we apply the field in a different direction, we can shift this bifield disk from the one direction to another direction. And when we did the analysis by putting this is analysis also a bit tricky. We have a special course in the Python we designed so that we can map this magnetization based on the shift of this bifield disk from one direction to another direction. And we can see that from the one direction we can map, this is the direction of magnetization. Direction of magnetization from the is here in this direction. Maybe I'll just take the pen. So you can see the direction is this direction. And after applying the magnetic field in this direction, we can see that the direction of the magnetization, the pomelo in this direction. So we are able to successfully demonstrate that. We can observe the switching, we can observe the domain wall propagations using the Institute of Optical Microscopy. With this, I would like to thank that the small step towards to design a digital world where we are trying to integrate all these different phenomena, spin transport phenomena on the single chip to make ultra dense and ultra fast bus. With this, I would like to thank everyone for their patience.
Thank you, Professor, for your nice, wonderful presentation with experimental demonstration. Also, we have really enjoyed the entire session. So, my first question is, you just talk about the spin current.
Yes.
So I have noticed that in your slide animation, the two spin directions are opposite.
Yes.
But the current direction is same. So in what way the current direction depends, Professor?
Okay. Let me go to the slide.
Yeah.
Okay. This slide, right? Okay. So in this slide, so can you just maybe let me repeat the question. So you are asking me.
Yeah. In next slide. Next slide. Yeah. Here.
Okay.
Yeah. I have noticed that here the spin direction is two different direction, but the current direction, spin current is in the same direction. JS.
Okay. You are saying because I'm talking here the two effects.
Okay.
Maybe I missed it, so I will explain it again. So in the first effect, what we are doing, we are trying to convert the charge current into the spin current.
Okay.
So the input is charge current. So this blue line is the input, which is a charge current, And when you have charge current, so what will happen, because the charge current is in this direction? So my as we know that the electrons are opposite to the charge current. So the electrons, like charge current is coming this way. The electrons, all the unpolarized electron, up spin, down spin electrons are coming from this way.
Okay.
So they're coming here. So moment they experience the spin orbit coupling. Okay, maybe I can explain the spin orbit coupling in more detail. So which is quite reasonable. We can see that maybe I just take the pen so it's easier. So spin orbit coupling is proportional to the P cross gradient of V.
Okay.
Very simple. And we know that this is just nothing if sigma is just an effective magnetic field, B effective, and which we represent, this is C cross was you can say that V cross E by C square is analogous to this. So this is the effective magnetic field experienced by these electrons because of spin orbit coupling. So moment they experience this effective magnetic field, so they have the effective magnetic field because of the material. So the spin down electron will try to go in the one direction and ups will go to another direction. So as a result of this, I will set up the another current, charge current direction, this. Now I'm in this one, the second side, what I'm coming with, now I'm saying that this inverse spin Hall effect measurements, where I'm talking about now my input is a spin current, because I have been telling from the beginning, spin Hall effect is converting the charge current to the spin, and inverse spin Hall effect is converting the spin current to a charge current. So now my input is this. So this my spin current is coming from this. So this is because when we have this spin current, one directional spin current which is being pumped. So because of the majority spins is accumulate that interface, minority spin accumulate at the interface. So we have a setup of the charge current which is in the opposite to this, orthogonal to that direction.
Okay, thank you.
Maybe I'll just bring my this camera.
Very nice presentation. We have really enjoyed a lot. And one participant is raised. Mr. Praveen, you can unmute. Mr. Praveen, you can unmute and you can ask a question. You have raised your hand. Okay, participants, you can ask questions in this regarding this talk to Dr. Rohit Medwal. Mr. Praveen, you have raised your hand and you can unmute yourself. Okay. Okay. If there is no question, means we can wind up this session. And really, I'm very thankful to you, behalf of the management and the Department of Physics, SRMIST Ramapuram campus. I'm really thankful for your nice presentation and spending your very valuable time in your busy schedule, sir. So thank you. Thanks a lot. Thank you very much.
Thank you, Dr. Rohit Medwal. This is the first time the digital universe topic I was able to listen. Very nice.
Thank you, Dr. Medwal, for nice presentation.
His mic is muted.
Rohit sir, your mic is muted. We have noticed the mic is muted.
Okay, sorry, I'm saying that thank you very much for inviting me. It's my pleasure. Definitely.
Okay.
Thank you so much.
I'm happy to contribute anytime next time also.
Oh, sure. You are welcome. You are most welcome.
Ultra fast digital universe.
Thank you. Thank you for that.
Thank you, Dr. Medwal, once again. Now, good noon to everyone present here. Thank you, Dr. Medwal. Shall I continue, ma'am? Okay. Oh, okay. Subramaniam sir. Subramaniam sir.
Ma'am, please wait, ma'am. Please wait.
Please make a co-host to Bina ma'am.